All right. So today is the second day of the Glorious Women Symposium. My name is Debarati Chatterjee. I am professor at the Inter-University Center for Astronomy and Astrophysics. I'm one of the organizers of this meeting. The other organizer is Professor Anuradha Gupta. So she's from the University of Mississippi, and she is also here at this session. What we are particularly doing in Glorious Women Symposium is we are talking about the different diverse aspects of gravitational wave astronomy. Yesterday, we had already, on the first day, we had a plenary session which had eminent speakers from the global collaboration. We had talks from LIGO-India Scientific Collaboration, from OSGRAV, from Virgo, from LISA, as well as from the International Pulsar Timing Array. So this was a very nice overview of the current status of gravitational wave astronomy across the globe. And yesterday we also had a panel discussion, a very interesting panel discussion on women representation in gravitational wave science. We plan to put the science talks on our YouTube channel, on the LIGO India YouTube channel. So I'm chair of outreach and education and public outreach for the LIGO India Mega Science Project. So if we have a permission from the panelists, maybe we can also put the panel discussion session online. So today we have again a slightly different flavor. So we will have first a focus session where we have talks on various multidisciplinary aspects of gravitational wave science. So first up, we will have a talk on particularly on gravitational wave instrumentation. This will be by Dr. Mansa Thirugyan Sambandam from IUCA. Next, we will have a talk about fundamental physics with gravitational waves, and this will be by Shilpa Kastho from Saha Institute of Nuclear Physics in Kolkata in India. We also will talk about multi-messenger astronomy, and Professor Samaya Nisanke from DAISY in Hamburg, Germany, is going to join us for this presentation. We will also have Professor Surabhi Sachdev from Georgia Tech University in the US talking about data analysis and searches in gravitational waves. And finally, we will have a talk by Professor Manuela Campanelli from Rochester Institute of Technology in the US. And she will tell us more about theoretical modeling and numerical relativity simulations. So we look forward to a very exciting focus session. Today, towards the evening, we will have, this is a 7:30 p.m. Indian Standard Time. I think we have participants from all across the globe. We will have, after the focus session, the final session will be an interaction session called Ask a Woman Gravitational Wave Scientist. So there will be opportunities for the participants to interact directly and ask questions to early career researchers, in particular about various aspects of gravitational waves, about career advice, and ask them about their career trajectory and so on. So I look forward to a very exciting session. So let's start with so Dr. Mansa Devi is already here. So Mansa, are you able to share your screen?
Yes. Are you able to hear me?
Yes.
Good evening, everyone, if you're in India, and good morning if you're on the other side of the world. Today, in the time given to me, I would like to give a brief overview of what we do in instrument science in gravitational waves. And I'm not the only woman who is involved in instrumentation. I've seen quite a majority of women, especially in the GW community in instrument science, compared to other experimental fields. So that's something that I'm proud of, that I have people prior to me who I can interact with and talk to. When I started, I went through the regular pathway of completing my bachelor's, master's, and then my PhD, everything in physics. And then for my postdoc, I was at Caltech working with the LIGO laboratory. That's where I was inducted into the GW community. And I've been with the GW community for more than 10 years now. And as of now, I work with the LIGO-India project, contributing towards the instrument science aspects of the upcoming detector. So, what I do in the GW instrument science community, mainly I do instrument science for gravitational wave detectors, but I'm in general inclined towards anything that deals with precision measurement in photonics-based devices. And that actually directly feeds into the gravitational wave detector itself, because the detectors, gravitational wave detectors that we have on ground are all based on interferometric gravitational wave detectors, and they use complex optical systems to detect gravitational waves. So in here, I've uh, majorly divided the subsystems that I work with in gravitational wave detectors. I'm trained to work in lasers and photonics by research. So that is my specialty or expertise, as one would say. And now I'm working towards quantum enhancements so that we are able to make more precise measurement and enhance the sensitivity of the next generation of gravitational wave detectors. So, for people who are new to knowing about what the instrument is all about, so interferometric gravitational wave detectors consider the base simple schematic is actually a Michelson interferometer. So, in here, if you see in a Michelson interferometer, you have a laser, and which is a coherent source of light, and from there, the laser light gets split into two paths which are orthogonal to each other, and you have highly reflective mirrors at the two orthogonal directions that reflects the light back. Depending upon how the waves interfere after they recombine, you will be able to detect either a constructive interference, wherein you see an enhancement in the amplitude, or a destructive interference if the peaks of and troughs of the waves do not match. Now, if there is a gravitational wave that is passing through an interferometer, which is locked at a particular position of these two waves, then you start seeing a superposition of the two laser beams being influenced by the incoming gravitational wave. So, so this is the base principle of all the interferometric gravitational wave detectors, regardless of where they're located. Uh, and but to make this detection, it's not as easy. So if you have a Michelson interferometer in your lab, it's not going to be able to detect a gravitational wave. And there are reasons for that, because the displacements that the mirrors experience by an incoming gravitational wave is very, very small. And it is actually a subatomic size displacement is what we are looking at. And that's the reason why we are not able to detect these gravitational waves on a conventional Michelson interferometer that you set up in any physics laboratory. So what do we, so why is that? It's because we are trying to detect a gravitational wave signal that is buried with the surrounding noise around the detector itself. So there are two sources of noise. One is the detector itself, the way you build the detector itself, in the laser, in the way you have mounted the mirrors, those itself induce noise. And then the different noise sources around it, for example, the vehicles moving around or people stomping around the lab. So these are what creates noise around the instrument. So in general, the gravitational wave signals that are passing around us go undetected, because the gravitational wave signal is actually buried in the noise around us. So when a gravitational wave detector is commissioned, it is actually installed in such a way that what we call is a locked state. And in the locked state, what you see is a fixed interference between the two waves that are recombining from both the mirrors. And what we are trying to measure is the influence of a gravitational wave, which means that all the noise sources around the detector have to be really, really small compared to the gravitational wave signal that you're trying to detect. And if we improve on the noise level, or how quiet your detector can be built, you obviously will increase the signal to noise ratio and have a better signal that you can detect. And once you are able to detect better signals, obviously your astronomical reach also increases and gets better. And that's how we detect gravitational waves in terrestrial interferometric gravitational wave detectors. But the actual interferometric detectors, as I said, is not just a laser beam splitter and two mirrors. In order to enhance the sensitivities, there are tricks that are applied and reduce the noise. There are other techniques that are applied. And if you would like a cartoonish layout, this is just looking at the important components of an interferometric detector. It would bring it down to this sort of a schematic, wherein you have a laser and then you have some components that actually condition the laser to have lower noise. And then you have a mirror helps to increase the laser power by increasing the sensitivity of the detector. And then what you have here is the Michelson that we talked about, which means that the end mirrors here along the X arm and the Y arm are the ones that are going to interact with the gravitational wave or be able to sense the displacement of a gravitational wave going through the interferometer. And then you have a signal recycling mirror, which actually helps tune the resonance or the bandwidth of the detector itself. And then you have other components that are actually introduced to reduce the quantum noise in the detector. We'll talk about a little about these noise sources as we go. And then we have an output mode cleaner that actually cleans up the light is being detected gravitational wave readout. So there I showed the most important components, right? And each of these important components also has subcomponents. For example, if you look at each of these mirrors, the important mirror, it is actually suspended by a quadruple suspension cylinder. It's a four-stage pendulum. And it's a quad pendulum, as we call it, that gives rise to seismic attenuation, which means that makes it immune to the seismic noise around it, reduces the seismic noise around the system, in the mirror itself. And then we have the signal readout that goes through a bunch of controls and data acquisition system, and then the data storage and data analysis part of it. But as you can see, there is a vacuum system as well. The whole system is enclosed inside vacuum, and there is residual noise that comes from the gas that is there in the vacuum. So there are several other components in the detector, and as you dig deeper and deeper, that is when you will come into sense that the instrument is actually a mega instrument, and that's why gravitational wave detectors are actually called mega projects, because it needs the level of sophistication and the level of expertise it needs is very vast, and that's why the GW community is actually is very interdisciplinary, in the sense there are experts in every field who actually come together and make GW astronomy possible. So when we talked about the different components, and each of these components, if I have to divide them into like major categories, there are optics, there are mechanics, and there are electronics. And there are things that we need to worry about if we want to make the overall noise in the detector really, really low. For example, in optics, we have mirrors, and you have to make the mirrors that we use are as large as 30 to 40 centimeters in diameter. So which means that the substrates that you use and the coatings that you use in these optics need to have a very high precision or should have a surface smoothness to such high ultra precision that you are able to make a gravitational wave detection, because any imperfections in this mirror actually can mimic a gravitational wave signal. Then we have the lasers itself. The laser itself has its own inherent noise, which is the frequency noise and the intensity noise in the laser that we talk about. Then we have photodetectors that convert the light into signals that we can actually measure. And there are the electronic circuits that go into it, into building these photodetectors, have to also be low noise. So we should not be adding more noise to the signal itself. Then comes the mechanics, which includes the vacuum subsystem, which includes the suspension system and the vibration isolation system, which give seismic attenuation. So when we want to build a detector, we have to look into all these components and then come up with what we call a noise budget. We have to look at the contribution of noise from each component of the detector, and then we come up with a noise budget. So what you see here is on the x-axis, it's the frequency. It is basically the noise, the noise distribution in frequency. And as you may know, if you've heard some of the previous talks, you know that terrestrial gravitational wave detectors make detection in the bandwidth of somewhere around far tens of hertz to up to a kilohertz. This is the most sensitive region that we're talking about. And our target is to reduce the noise from the different components of the detectors in this region of interest. And going below in the frequency, if you go lower in the frequency, it is very difficult for us to reduce the noise in those frequency regions, mainly because we're talking about terrestrial detectors and there is only some amount of seismic isolation that can be brought about in a terrestrial detector. And if you want to detect gravitational waves in the lower frequencies, that is where the space-based gravitational wave detectors come into play. So with a terrestrial ground-based gravitational wave detector, you will be able to make detections only in the region of interest that the current detectors are operating at the moment, unless technology pushes it uh, uh, and gives us a breakthrough. So as you can see now, what you see in this curve is the black curve is the curve that actually shows what is the total noise that we have in the detector. And you see, from the plot that you can see, there are two main contributors to this total noise. One is the coating Brownian noise, which comes from the Brownian motion, Brownian noise in the mirror coatings that we have. And then we have the quantum noise, which comes from the quantum nature of light itself, because we use light to finally sense a gravitational wave signal. As you saw, there is an interference between two waves that comes back and recombines at the beam splitter in the Michelson interferometer. So since we are using light as a measurement tool, the quantum noise, the quantum nature of light comes into play, and that gives rise to the contribution of quantum noise. And these are the two noise sources that the current instrument scientists are working towards reducing. You have other noise sources. For example, you see this excess gas noise that is in there, that is way below there. So people don't worry about those noise sources. And what we do when we want to build a detector is, once we've assembled the detector, we go noise hunting. We look for where the noise sources are coming from, the different components of the detector, and then work on that component to increase the sensitivity of the detector. So that was the part where I wanted to give a general overview. And then I thought I would actually focus on parts of the detector that I work on. So one of my main area of work in the GW detector or in the LIGO-India detector is to to build the PSL, or the pre-stabilized laser, which is the laser source that you find in the interferometric gravitational wave detector. So the pre-stabilized laser is one of its kind, and mainly because the noise levels of this laser, it is the quietest laser in the world. So the laser noise in here is coming from the fluctuations in the frequency of the laser and the intensity and the spatial stability, which means the position of the beam. Because as the position of the beam changes, it changes its position on the mirror and that we are trying to measure. So any phase shifts that we see in the laser gets converted into fluctuations at the GW readout port. So which means that we need a really quiet laser, and this is what we're working on right now. So that's one area that I work on. There are different stabilization loops that run across to keep this laser the quietest possible one on Earth. The other region that I work on is dealing with the quantum noise in LIGO. This is of interest because, as you saw, this is one of the limiting noise sources of the instrument. As you know that in a Michelson interferometer, we make our detection by looking at the fluctuation of the light at the dark port, intensity fluctuations at the dark port. So if you look at the normal light wave that comes from a laser, ideally we draw the light wave as the electric field as a smooth wave. But in reality, even if we have the best coherent source, it is not a smooth wave. There are fluctuations. There are fluctuations in the amplitude, as you see at the tips. And then there are fluctuations in phase. And the phase noise manifests itself across the zero crossing of the electrical field, as you see. So the zero crossing is no more a point, but a region over which you have a zero crossing. And that is what we call as the phase noise. So now if you want to represent the coherent source as a single point in the amplitude and phase space, what you have is it's not a point, but a fuzzy structure, and that is how a coherent source is represented. So the laser light that we see is actually a distribution in amplitude and phase. But this is a noise source. This is a fundamental noise source because we're using the light state, the light as our tool to measure. So one way to overcome this is by using what we call squeeze states of light. And so the fuzziness that you see in the amplitude and phase, the smallest area of this structure is determined by the Heisenberg's uncertainty principle. And as we know, there is always an uncertainty. If you try to measure the phase, there is an uncertainty in the amplitude. So what we try to do is while the uncertainty principle defines the area, it does not define the limits on the phase and amplitude independently. So since our interferometers measure the phase of the light that is returning, so trying to measure, we can actually use a coherent source wherein we allow the amplitude to have a larger variation compared to the phase. And which means that we allow for more uncertainty in amplitude and reduced uncertainty in the phase, which means reduced noise in the phase. So if you have a coherent source, the wave would look something like this. But now if you have squeezed it in amplitude, you will see that the zero crossing points are rather large. But if you look at the amplitude points are where you see less noise. And if you consider a vacuum state, which is no light, for example, there is no light that is entering the interferometer from the detector port. So the vacuum state itself has some inherent noise that is around it. And what we inject into the interferometer is squeezed vacuum, which means, as you see here, there is actually the fluctuations across the zero crossing points are actually reduced to a minimum, but the amplitude uncertainty increases. So what has quantum squeezing allowed us to achieve? So in this plot, if you see the measured total reference noise is given by the black curve in here. and the measured squeezing local noise also is given in here. But what you see in here is the model of it, and what you see is there is a crossing across which you set the standard quantum limit of the detector, which means that you will not be able to, it's a fundamental noise source. So you have to be able to compensate and or at least try different tricks so that you will can make a measurement which is below the standard quantum limit that is set to the detector. And that is done by squeezing. And LIGO has been able to achieve 3 to 5 dB. With 3 to 5 dB squeezing, we have increased the detector range by 15 to 18%. But this does not stop here. It's not that we are satisfied with this level of squeezing, because most of our future gravitational wave detectors rely on squeezing as one of the contributors to have better sensitivity. For example, the US-based detectors, the next generation of US-based detectors target squeezing up to 10 dB levels. And the European detector, which is the Einstein telescope, also targets a 10 dB effective squeezing. And as you can see along the timeline for the Cosmic Explorer, squeezing is something that is still people are working on to improve the sensitivity of the instrument itself. The last one that I work on is, this is more fun, that I got involved in after entering instrument science in gravitational waves, is interferometer sensing and control. While the laser and the squeezer are independent subsystems, interferometer sensing and control is something that's global, that looks at the entire instrument itself. So when I showed the schematic earlier of the gravitational wave detector, you saw the laser, and then you saw the different important mirrors that are there uh, in the optical layout. And we talk about a single light that is going across the entire interferometer. But if you can see that actually since we are measuring phase, that is very much dependent on the different lengths, cavity lengths inside the interferometer, it is important that these mirrors are held in such a position that you have an entire, a full control of the different degrees of freedom of the interferometer. And that cannot be done by a single laser. So because of that, there are several techniques that are employed to actually measure the optical phase in different regions and then be able to sense the different lengths so that you can keep the interferometer in a locked state. And this is a very fun part, because once you have the instrument, you are working on the instrument. After it's installed, you work on the instrument and try to improve its sensitivity. And this happens over years together. It's a years of work that goes in looking at the instrument, hunting for noise sources, trying to find a way wherein you can sense and control the lengths effectively so that you are able to make better detections. And that's where I would like to conclude. Thank you. If you have any questions.
Thanks a lot, Mansa, for this very nice talk on, particularly on gravitational wave instrumentation. So let's see if there are questions on chat. Please type your questions on chat so that we can try to respond to some of them. In the meantime, I have a question. I think one of the participants asked this yesterday, like we are going from 4 kilometers now on to 40 kilometers, like we are going an order of magnitude, larger. So what are some of the steps that we would like to, uh, what do you foresee? Like what are some of the challenges and how do you overcome that as we go forward?
So one of the major challenges when you upgrade from 4 to 40 is the logistics itself. So because
Right,
we are on ground and our Earth is spherical, so
right,
if you have to, and light travels in straight lines, right? So which means that you have to make a straight line of 40 kilometers, which means that you have to dig Earth and move Earth. One point is finding a place which is 40 kilometer by 40 kilometer in a quiet zone, which is not disturbed by the population around it. So which means you have to find a space that doesn't have a lot of environmental noise or as or the human living noise, human noise around it. The other part is moving Earth that gives you the light to go across 40 kilometers across and bounce back. The other challenge that we have is, as you know, light has its diffraction limit, right? So even if you have a coherent source, it eventually expands across. So which means that at 40 kilometers, you will need larger mirrors, which was the beam size will be larger, which means that you have to work on coatings for the larger mirrors. So there is a lot of technology challenges that we have in taking it forward from 4 kilometers to 40 kilometers. This is a very challenging jump.
Right. I mean, we have to correct for the curvature of the Earth and also losses in the laser power. I mean, there's so many things I can
Yes,
think of, right?
yes,
So,
yes.
yeah,
Every subsystem has to incorporate a change or will be faced with a challenge when we make that jump from 4 to 40 kilometers.
right. Okay, I see one question in the chat. Um, can laboratory Michelson interferometers be used or modified in any way to detect gravitational waves?
Yeah, so for this, I would like to bring the example of several prototypes that we have in different GW labs around in the collaboration. While these Michelson's interferometers or modified Michelson interferometers, the prototypes are in the exact same configuration, optical configuration as the main detectors. But the main caveat that we face is trying to reduce the noise around the instrument, which means that if you have a really, really loud gravitational wave, then you will, which is above the signal to noise ratio or the sensitivity of the Michelson interferometer that you try to build, then you will be able to detect. But unfortunately, we don't have any sources around us that can create such a loud gravitational wave to be able to detect on a conventional Michelson interferometer that we have in the laboratory. So even if you build a Michelson interferometer in your laboratory, they will also have the same noise budget curve that I showed you, and the lowest point will not be of the order of 10 minus 22, but it will be higher than what you expect. So for example, some of the prototypes operate at 10 minus 15, 10 minus 14. So which is not a place where you will find a gravitational wave signal that loud.
There are also some of these bar detectors, like also
Yes.
spherical detectors, right? Mini grail and so on.
So
I don't know.
bar detectors were at some point in history something that the GW community worked on. So basically, the bar detectors are installed, and again, they look for the same stretch and squeeze effect that a gravitational wave would produce on a solid bar. But the problem with those is the limitation there is when you keep any solid object, the solid object will have its own frequencies, body mode frequencies, as we call, that will interfere with the range of the detection that you see. That's why people got excited when the lasers were invented. People, okay, this is a tool that I can rely on, and that is independent of the physical nature of the tool itself. So we are, again, there are also torsional bar detectors, people that are working on. There are different other types of instruments that have been suggested in the past, and some that people currently work on. For example, atom interferometers are something that people currently work on. So the interferometric gravitational wave detectors are the only ones who have made a successful detection.
Thank you very much, Mansa, for this very exciting talk.
Yes.
Okay,
Thank
so I
you.
think in the interest of time, we will move on to the next speaker. If there are any other questions for Mansa, maybe you can put it on the chat, and if she's around, she can try to answer them. All right, so let's move on to the next speaker, and it is so it's Professor Shilpa Kastur. So Shilpa, can you share screen?
Yes, I hope you can hear me clearly.
Yes. So give me a second to spotlight you.
Yeah. Okay.
Yes, we can. Do you want to go to full screen? Yeah. Okay, perfect.
Yes. Can you see my screen? Changing the slides?
Yes.
Okay. Okay, so first of all, thank you, Debaroti and Anuradha, for inviting me to this inspiring celebration of curiosity. And after such a nice summary of the instrumentation part of the gravitational detectors, my talk will start from the point where we have already detected the gravitational waves from the compact binary mergers. So thanks to Manasa as well for setting the stage for me. Yeah, so gravitational waves are basically tiny ripples in the fabric of space-time, which travels at a speed of light. And these waves can be generated by accelerated mass with having time-varying quadrupole moment. And as these waves passes through the masses, it squeezes or elongates the object. And that's how we detect these waves on Earth. Right. So here, what you will see is basically the merger of two black holes and the corresponding signal that we can observe on Earth. Now, the better we can model this waveform is the better we can detect the physics of the binary system, the properties of the source. Now, here, what you are seeing is the two black holes moving around each other, and their spin angular momentum is not really aligned with orbital angular momentum directions, and that's why the orbital plane actually precedes. And corresponding gravitational waveform is what you are seeing in the bottom panel. And because of the orbital precision, we can also see, along with the increased increment in the frequency, you can also see a modulation in the gravitational waveform. So that signifies that the orbit of the binary is actually precision. Right. So currently we are in the era of ground-based gravitational wave detectors, as Manasa mentioned in her summary. And so we are detecting the stellar mass compact binary mergers through these detectors, which are operating in the frequency range of about 10 to 1000 hertz. Right. So now the first direct observations happened in 2015 through GW 150914, and since then there has been total 4 observing runs, which concluded in by the end of 2025. And in all of these observation runs, we could see a constant increase in the sensitivity. And that reflects by the fact that the total number of detections has actually increased over these observing runs. For example, by the end of second observing run, the total number of detection was only about 17 or so. And by the end of third observing run, it was about 90. And now the number quoted in the website is actually 368. So so nowadays we are detecting a huge number of these compact binary mergers. Now, in this plot, what I'm actually showing is the detected compact binary mergers through gravitational wave detection. So the blue dots are the binary black hole mergers, and the orange dots are the neutron stars present in a binary merger. And here is what I'm showing is the detection from the first part of the fourth observing run in the plane defined by the primary and the secondary mass. And you can find that the new detections are colored by the blue dots, and the gray dots are actually the old detections in the 3 observing runs that already happened in the previous years. And you can see that you can see where the 150914 is somewhere around primary mass about 36, and the secondary mass was about 29 or so. And you can also see the highest mass detected here till the first part of the fourth observing run towards the corner of the of this plot. So I think even after 10 years of the direct detections, we cannot give a talk without mentioning once about GW150914. This event was such a perfect event which stayed in the band for about zero point 0.2 seconds, and the signal increases in the frequency from 35 hertz to the peak amplitude frequency, which is about 150 hertz. And it was detected on 14 September 2015, where the signal first arrived on the Livingston detector, and then after 7 milliseconds, it arrived on the second detector, the Hanford one. Now, after saying that, what I want to mention here is, besides the gravitational wave transient catalogs by LBK collaboration, there exist two more catalogs which was constructed using the public data. But all these three catalogs are more or less kind of consistent with each other, with very minor differences in between them. What I want to highlight is the IAS analysis actually reported that using higher harmonics in their search, they can find a few more new detections. So what I want to say is what I started my talk with, on the note that the finer waveform model that we use, we can dig out the better physics, we can dig out the source properties in a more better way. Now, gravitational waves actually gives a wide opportunity to test GR in the strong field regime. That's what I am trying to show you here, where the different candidates for testing general relativity is plotted in a plane defined by the typical field strength, and along the x-axis, which roughly goes as the typical mass over typical length scale of the system. And the y-axis is defined by the curvature strength, which roughly goes as square root of m over L cube. And as you can see, that the detection by the gravitational wave detection by the ground-based detectors lies on the top right corner, which is in the strong field and the strong curvature regime. So you can clearly guess that this gives the excellent opportunity to test GR in the strong field regime. Now, there are different ways that one can modify the general relativity. We can introduce massive graviton theory. One can introduce different additional fields, the scalar fields, vector fields, or the tensor field. One can also try to break the basic assumptions, for example, Lorentz violation, non-locality, or even introducing extra dimensions, etc. Of course, these are not exclusive. For example, one can have theories where you have an extra tensorial field, and as well as massive graviton, for example, biometric theories of gravity. But I mean, there exist a few theories where there are numerical simulations, few modified theories where there are numerical simulations. There are analytical waveforms at the leading order as well available for some of these theories. But of course, these waveforms are not exhaustive enough to cover the whole space of this modified theory roadmap. And since we have started detecting these gravitational waves, we also do not expect that the waveform will be very different from some general relativity. And so, since we already have the data, the best option to dig out the modifications is through model agnostic tests. By model agnostic tests, I mean that we can introduce some deviation parameter, some ad hoc deviation parameter at the level of waveform model, and try to fit our data with that modified waveform model and try to dig out what is the bounds on those deviation parameters. One can also perform the consistency tests by checking the consistency between the lower frequency part of the waveform to the higher frequency part of the gravitational wave from these compact binary mergers, and try to see if they are consistent with each other. Now, there are plenty of analyses that are going on and that are being performed on the current detections. I will, of course, not be able to summarize all of them, so I'll try to focus on few of them. Before going into the details of few of these tests, the central ingredients that we need for to perform these tests is the gravitational waveform. Now, the waveform that we use for the current detections can be divided into three segments. The first one is the inspiral regime, where the two compact objects are far away from each other but orbiting around each other. The emitted waveform is modeled within the post-Newtonian theory. The second part is where the two objects merges, is known as the merger and can be modeled with numerical relativity techniques. And the last part where the merged object slowly settles down to a stable curved black hole can be modeled with black hole perturbation theory. And that part of the waveform, we call it as wind down. Now, the first few tests that I'm going to talk about is using the inspiral part of the waveform. The first one is the test of post-Newtonian theory. So as I mentioned, the post-Newtonian theory explains the waveform in the inspiral regime. The post-Newtonian theory is basically a collection of or a mixture of various analytical approximations to model the gravitational waveform from the compact binary inspirals, which is written as a series in the post-Newtonian expansion parameter V over C. Now, this post-Newtonian expansion parameter to the leading order, you can think of this V as the orbital velocity of the binary. But as we go to higher and higher order, the notion of this orbital velocity is lost, and you can think of it just as a perturbation parameter. Now, what I have shown here in this equation is the gravitational wave phasing written as a series through post-Newtonian coefficients, where the different phi k's are the Pn coefficients at different post-Newtonian order. Now, if the underlying theory is not GR, then one can expect that these phi k will be different as predicted by GR. Now, this difference can be modeled with some ad hoc parameters, delta phi k. And with these modifications, one can again ask the question, what are the bounds on these delta phi k's given the data of the gravitational waves that we are observing nowadays? In the adjacent plot, what I have shown is the statistical bounds on these delta phi k's at different post-Newtonian order. And as you can see that the best bound is on the dipolar part or on the -1 PN term, which arrives due to dipolar radiation. And as you go on to higher and higher post-Newtonian order, the sensitivity to these parameters decreases because the contributions from the higher orders are less. So the bounds on the higher order parameters increases. And these are the results that has been obtained using the events in GWTC3, which is denoted by the blue diamonds. The second test that I will talk about is the test of spin-induced quadrupole moment. Now, if the compact object is, so it's a test of the multipolar structure of the compact objects. Now, suppose the compact object is spinning. Due to its spin, there exists a spin-induced deformation in the multipolar structure, and it appears at 2pn order. Now, the spin-induced quadrupolar scalar that appears at 2pn order is of the form what I have shown here in the first equation, which is proportional to the spin of the compact object and the mass of the compact object, as well as with a constant scalar kappa. Now, this kappa parameter takes the value of 1 for a curved black hole, as we all know by Noether theorem that the astrophysical black holes are completely defined by the spin and the mass of the black hole. This kappa can take a value about 2 to 14 for neutron stars, and it can be as high as 10 to 150 for spinning boson stars. Now, one can ask, given the data, one can ask the questions that what exactly these kappa are for the binary systems that we are observing today. And that's what I am showing here in this in the plot, where the plot shows the posteriors on the symmetric posterior on the deviation of the symmetric combinations of these kappa for the two component object. And as expected, the deviations is consistent with their value being zero. So the system that has been analyzed through this test actually says that what we are observing is a binary black hole merging. The third test the third test that I'm going to talk about is a kind of generalization of the test of spin-induced dipole moment. So what one can ask is whether the multipolar structure of the compact binary systems are consistent with GR or not. Now, the gravitational wave phasing and amplitude can actually be represented by the multiple moment of the system. Now, one can ask that if the theory is not GR, then one can assume that these multiple moments are different than GR, and that difference can be assumed as a scaling factor to these multiple moments. And we can compute the gravitational wave amplitude and the phasing expressions along with these modifications and try to ask this very same question that given the data, what are the bounds on these multipolar coefficients? Having discussed about the different in spiral test, the next test that I'm going to talk about is with the ring down part of the waveform. Now, the ring down part of the waveform is modeled using black hole perturbation theory. And it can be written as a superposition of damped sinusoids, and these damped sinusoids are known as quasi-normal modes. Now, the quasi-normal modes are defined by its amplitude, A, L, M, N, and its complex frequency, omega, L, M, N. Now, this complex frequency can be solely determined by the mass and the spins of the astrophysical black hole. When we can dig out multiple of such modes from the data, we basically call it black hole spectroscopy. Now, the general belief around 2010 or so was we need at least LISA type of sources for which we can perform this black hole spectroscopy. But with a more updated population model, people have showed that we at least need LIGO-Voyager kind of a detector to detect a source with having multiple quasi-normal modes, with having detectable multiple quasi-normal modes. But with the detection of DW 190521, which was the most massive detection till the third observing run, we could perform the black hole spectroscopy. So what we did is we took the data after the merger for this event, GW 190521, and we tried to fit it with two arbitrary damped sinusoids with having independent frequencies. What we found is one mode with having frequencies about 60-ish or 62 hertz. And we also found a second blob in the frequency range of about 90 to 100 hertz. Now, if we consider that the mode that we are observing with the 60-ish hertz corresponds to the quadrupolar 220 mode, the second blob actually coincides with the expected 330 mode from our GR notion. So we can say that there exist two quasi-normal modes in the post-merger data of GW 190521. After this agnostic search, we also performed rigorous searches with Kerr quasi-normal modes, and we find that after about 6 or 7 milliseconds, the waveform, the signal is best fitted with two quasi-normal modes, having this 220 and as well as 330 mode. Now, as I said previously, that these quasi-normal modes are, the frequency and the damping time can solely be depicted by the mass and the spins of the black holes. Now, once we dig out the 220 mode, one can find the bounds on the mass and the damping mass and the spin of the remnant object, and one can use the second subdominant mode to ask the question whether there exists an extra hair for the astrophysical black hole or not. And we model that extra hair by a deviation in the frequency of the subdominant mode. We also try to fit the data around the same time with the deviation in the frequency of the damping time of the 230 mode. And we found that these deviations are consistent being zero. Right. So this was another event which was detected during the fourth observing run, GW 250114, for which the component masses are very similar to GW 150914, but this event has quite a large network SNR of about 80, almost 3 times the SNR of GW 150914. And so before going to GW 250114, I want to mention about GW 150914, where people showed that if we analyze the data starting at the peak time where the 2-2 mode peaks, one can see the 220 dominant 220 mode along with the overtone associated with this 220 mode. Now, it's not really right to fit a linear perturbation theory starting at the peak frequency. So people were skeptic about whether we should really say that there exists a overtone or not. And that got resolved with the detection of GW 250114. And what LVK has shown is the existence of the overtone 221 associated with the 220 mode for a prolonged time after the peak time. Now, having talked about the black hole spectroscopy, I'll briefly mention about the consistency test, which widely known as in-spiral marginal consistency test. As I said in the beginning of my talk, that in this consistency test, what is actually being done is we compute the masses and the frequency, we compute the mass and the spin of the component object, and we compare it with the higher frequency part, and we compare it with the masses and the spins estimated using the higher frequency part. And people have shown with different gravitational waves detected in GWTC3 or GWTC1, or even during the first observing run, that the difference between the masses estimated from the lower frequency part and higher frequency part is consistent with zero. This in-spiral marginal ring down test can also be posed as the test of black holes area theorem, where one can construct the initial total area of the two black holes and compare it with the final area of the remnant object. And for the same GW 250114, people have shown that the final area of the black hole actually increases. And so GW 250114 obeys Hawking's area law. So story so far, I have talked about a few in-spiral tests, namely parameterized tests of post-Newtonian theory, spin-induced quadrupolar test, also the parameterized tests of post-Newtonian multipolar structure. I have discussed about the ring-down test that has already been performed and showed some of the results that has been obtained in past 2 or 3 years, and also the consistency test and the test of black hole area theorem. So just to end the discussion from my side, we are detecting growing families of binary black holes. The major questions with respect to the fundamental physics that are being asked these days is, of course, the nature of the theory, whether it's Einstein's gravity or there is a modification to this theory. We are also asking the question whether the black holes have extra hair or not. So to end my discussion, we have a lot of information from these events. So it's our duty to really dig out the physics out of these detections. Thank you. for listening. And if there is any questions, I'll be happy to take.
Yeah. Thank you so much, Shilpa. This is a very informative and interesting talk. We might have time for one question. So I'm going to read that from the chat. It is from Unnati
Okay.
Bhandari. And if you feel answering that, if you know the answer. Given current observational capabilities, do you think photon ring measurements could ever rival gravitational wave in testing GR, or will they remain complementary?
That's a very interesting question. Um, Certainly, the quasi-normal modes that we are observing is in the linear regime, so it's probably the deviation in the photon ring will not be possible to measure at this point, but who knows with a more sensitive detectors or for a more louder events, if we can see some deviation in the frequencies of subdominant modes, maybe we dig out something about the photon ring.
Yeah, thank you, Shilpa. As far as I know, I think the photon ring measurement Unnati is mentioning is from the Event Horizon Telescope, but those are
Yes.
different kind of regime. Like they are supermassive black holes, and what black holes we are seeing at the moment with ground-based detectors are smaller black holes. So maybe with LISA,
Mhm.
it might be possible when we start seeing massive black holes, and there might be a possibility of photon ring measurement with LISA. Yeah.
Mhm.
All right. Thank you, Shilpa, for so much for this talk. And I know you are
No.
in US and it's early for you, but thank you for being part of the symposium. Maybe then now we can move on for the next talk. So over to you, Durvati.
Thanks a lot again, Shilpa, for this wonderful talk on fundamental physics with gravitational waves. So next up, we have Professor Samaya Nisanke. Give me a second to spotlight you. All right, yeah, we can also see your screen. So yeah, the stage is yours.
Thanks so much. So I'd really, good afternoon, everyone. Good evening, everyone in India. It's such a pleasure to be here, and thank you very much to the organizers for inviting me to give this opportunity and also to celebrate International Women's Day with you today. And so I'll be talking about multi-messenger astronomy, and what I hope to do in the next 25 minutes is really give a broad introduction into the field. But I'll begin with a few words because it's International Women's Day about myself. My name is Samaya. I'm an astrophysicist. I'm also a mother of two really energetic children, a 2-year-old and a 9-year-old, as you can see there, a wife as well as a daughter. I was born in London in the UK. My father's from Sri Lanka and my mother is from Japan. And I grew up basically in the UK until I was 23. And I've been working on gravitational waves for now 25 years or so. So I think probably some of you are maybe younger than actually the amount of time I spent in gravitational waves. I've worked on mainly theory and observation and data analysis on different aspects, which I'll mention in my talk. But essentially, my trajectory and my career trajectory has seen me mainly traverse Europe as well as North America, and most recently in the Netherlands as well as of last year in Germany. But what I'd really like to stress is that over those 25 years, I would say broadly speaking, it breaks into two parts. Number one, the part before gravitational wave discoveries, which were quite challenging actually. There was a lot of interest in gravitational waves, but most physics and astronomy colleagues thought that it would be a while and maybe even decades before we would be able to detect them. So there was a lot of challenges, I would say, in finding positions, in finding jobs, also in having a family. So I just wanted to stress that. But of course, this all changed in 2016 when the first gravitational wave from a binary black hole, as you heard in the previous beautiful talk, was actually announced. And so since then, so just to mention a little bit about my career trajectory, and also that the work that I'll be discussing has been done by my wonderful group members in Amsterdam, as well as now in Germany, as well as in large and smaller gravitational wave and electromagnetic collaborations, as well as many collaborators listed there. And I will essentially follow this talk outline, and without further ado, because of the time limitation, I will begin by briefly introducing the compact object merger and our sources that we are interested. So as you just heard, over the last decade, we have observed at least 220 compact object mergers. So these are binary black holes, neutron star black hole, and binary neutron star mergers in gravitational waves. What you're seeing here in blue and the orange bubbles are those black holes and neutron stars that we have observed with the LIGO, Virgo, as well as CAGRA detectors. And on the y-axis, this is the masses in solar masses. The horizontal axis does not have any significance. And the pink and the yellow bubbles are the previously inferred masses for black holes and neutron stars, respectively, that were observed in X-ray and radio. And so there are a few points I'd like to mention. Number one, that we're really uncovering this diversity in the fundamental properties of these black holes and neutron stars. Secondly, that there are open questions as to what exactly is the nature for some of these low mass neutron star or black hole progenitors, as well as remnants, as well as previously hypothesized mass gaps. And thirdly, as these have been the focus of my work over the last 20 years or so, I'll be focusing on those neutron star black hole systems where at least one of the object has matter in the form of a neutron star, and where we may expect there to be delayed matter outflows during the complicated merger that are responsible for the electromagnetic observation that we are potentially going to be observing, as well as have observed. And I'll be really zooming into this one event, GW 170817, our first binary neutron star merger that we observed in both gravitational waves as well as in every part of the electromagnetic spectrum. And to date, this remains our only multi-messenger event that we have been able to actually pinpoint this gravitational wave merger for the first time in the sky. Okay, and so this is GW 170817, and this has allowed for multiple firsts that I'll be discussing in this talk. The first time we were actually able to use this to constrain Hubble's constant, the first association of a short gamma ray burst with a binary neutron star merger, the first time we were able to actually identify one of the astrophysical sites of our process, heavy elements, as well as the first tests of speed of light and gravity. And what I'd also like to stress is that this one event is impacting many diverse fields in astronomy and physics, as you have heard in the previous talks. And this is really thanks to the decades as well as thousands of individuals that have allowed for these advances in gravitational wave detectors, time domain astronomy, as well as in big data and machine learning. So it's really this convergence of the field. And as we heard in the previous talks, these gravitational waves, what we're measuring is this dimensionless gravitational wave strain, h of t, which has this 1 over distance to the source dependence. And these detectors, these laser interferometric detectors, are measuring a linear combination of the two polarizations, H plus and H cross, which are weighted by the detector antenna function. And we now have this worldwide network of detectors, of ground-based detectors, the LIGO detectors, the Virgo detector in Pisa, which I'm associated with, as well as, of course, the CAGRA detector in Japan, as well as, of course, really excitingly, we're all sort of at the so super excited and thrilled about the prospect of LIGO-India. And the reason for the importance of actually expanding our worldwide network, one of the key science drivers is really to be able to localize these sources on the sky with gravitational waves in order to do follow-up with other astroparticle and electromagnetic observations, and to do multi-messenger astronomy, as I'll discuss. And so just a reminder to make sure we're on the same page. What are we learning from gravitational waves? Well, from the gravitational waveforms that you heard in the previous talk, which are broadly speaking comprised of these three phases, the in-spiral, the merger, and the ring down, by essentially match filtering these theoretical and numerically obtained waveforms, we can actually not only detect the source, as you'll hear in the following talk, but actually infer the following parameters. So I really want to stress this is the information that we are learning from gravitational waves: the redshifted masses, the spins, the tidal deformability, the eccentricity, as well as geometric properties such as where it's happening in the sky, the source position, the inclination angle, as well as the luminosity distance to the binary. And how well we can actually measure these parameters depends on degeneracies between these parameters, the signal to noise ratio of the event, how much information is actually in the signal compared to the noise, as well as actually the frequency bucket of our instruments, of our detectors, as you've seen in the previous talk, are actually more sensitive to a particular epoch in the waveform, be it the in-spiral or the merger or the post-merger. And this depends on the masses of the system, and this will impact how well we can measure these parameters. So one big task in the community is to really input more physics, as well as environmental effects into these waveforms, as well as look actually at producing these waveforms beyond GR. And then the other aspect, and important and critical for electromagnetic follow-up, is the analysis. So typically we're using random stochastic sampling techniques such as Markov chain Monte Carlo or nested sampling to actually do the inference of the parameters. And this can take hours to days to weeks time scale, depending on the complexity of the waveform model. And so therein lies a huge opportunity where machine learning, in particular simulation-based inference, has come into play to actually speed up this analysis by several orders of magnitude. Now let's move on to GW170817, this first binary neutron star merger, which had a signal to noise ratio of 32. So it's one of our loudest events that we've seen. And the story really begins in the first 2 seconds, where what you're seeing in the middle panel on the very left is the gravitational wave spectrum that lasted about 100 seconds. In this power time frequency power spectrogram, as well as 1.7 seconds later, a short burst of gamma rays was observed by the Fermi and integral satellites. And I'll discuss the science that we were able to do within that first 2 seconds. But in order to actually localize the source, we really relied on the gravitational wave information. And so what's important to note is these L-shaped interferometers in themselves have very poor sky localization. They have quadrupolar antenna function, so they have all sky sensitivity. So we really rely on having a network of these detectors in order to actually use the time of the arrival times of the signals at the different detectors to reconstruct using triangulation where the event is happening. So in the case of GW170817, we were able to localize this source to 30 square degrees, and with the distance information, because we have this 1 over distance to the source dependence of 40 megaparsecs, this allowed observers essentially to reconstruct the gravitational wave volume and cross-correlate this volume with known galaxy catalogs ranked either in terms of the B-band or luminosity or their mass, and allowed for the identification at 10.8 hours after the actual chirp was observed of this bright blue flash seen in the galaxy NGC 4993 by the SWOPE telescope in Las Campanas in Chile, which was independently verified in the subsequent hour by several other independent groups. And this triggered the localization of this bright blue flash triggered this unprecedented observational campaign with over 100 instruments, both on the ground and on the space and in space, to actually observe this event. And this remains actually the most studied and data-rich transient that we have so far, and it's still being currently observed. So what you're seeing on the right is a plot from Kunal Mooley. This is the flux spectral density as a function over the first few years of the different detections that happened in the UVOIR in the first set, as well as then the afterglow observations that were seen with the radio and the X-rays. And what I'd really like to stress is that what made this compendium of observations just so beautiful is that they agreed at zeroth order with this prediction that there should be two different types of matter outflows, which resulted in the two electromagnetic counterparts that were seen with this event. Number one, the so-called kilonova, this rapid neutron capture nucleosynthesis powered transient that's thermally emitting on the hours to days to a couple of weeks time scale in the ultraviolet, optical, and infrared. And this, as you can see in the beautiful, I hope this works, in the beautiful movie in the bottom left, these are observations from the VLT X-shooter observations that essentially indicated and confirmed that this was actually the astrophysical site of our process heavy elements. The second electromagnetic counterpart that we were able to identify was to confirm the hypothesis that binary neutron star mergers themselves are the progenitors for short gamma ray bursts. And there was a plethora of amazing observations. I'm just going to focus on one that was taken by VLBI measurements at two different epochs in the subsequent year that allowed us actually to constrain the inclination angle independently of the gravitational wave information to 20 degrees or so. And I'll discuss why that's important scientifically in terms of what information this could provide. And so one big task on the computation, on the computationally astrophysics side is really to model all the different microphysics that are happening at different time scales, as well as different length scales, to really be able to do this joint characterization that I'll discuss. But there are many open questions, despite the amount of data that we have from this one event. For instance, we still don't understand what actually produced the relativistic jet that was seen with the short gamma ray burst, or if indeed we need to form a black hole to actually launch the jet, or indeed also why was the kilonova seen as such a bright blue flash initially. This was somewhat unexpected from the opacities that were predicted for our process elements. But combining these three gravitational wave as well as the electromagnetic information, I'm going to focus on three results that I think are particularly beautiful. Number one, those first 2 seconds. So there you hear the chirp. And there was the short gamma ray burst. And this allowed us to actually constrain the speed of gravity to light to 1 part in 10 to the 15. So already showing the power within those first 2 seconds. The second aspect is that neutron star mergers themselves actually allow us a unique probe of the QCD phase diagram in the high density, low temperature regime, and may allow us actually to map out the phase transition between hadronic matter as well as quark gluon plasma. And indeed, what you're seeing on the right in this seahorse shape are the 50 and 90% confidence intervals in the mass radius plot for neutron stars that we were able to constrain with this GW170817, its kilonova, as well as the second binary neutron star merger that was observed in gravitational waves, as well as two rotationally powered pulsars that were seen by the NICER satellite, as well as XMM, as well as radio observations. So really just to stress stress that we are able to constrain the equation of state already with these observations, but we need about 50 or so to really start to pinpoint the actual equation of state. In terms of, and what you're seeing on the underplotted lines here, colored lines, are the theoretical equation of state predictions. The third aspect is that one of the most basic endeavors in astrophysics or astronomy is to actually measure the distance out to various objects in order to actually map out the universe's expansion history. And so in the case of gravitational waves, what's beautiful is that we are able to actually have an absolutely calibrated measure of the luminosity distance. And from the electromagnetic counterpart, in this case, the optical counterpart, we could infer the redshift. So actually constrain the so-called Hubble constant, which denotes the energy densities of the different components of our universe. And so what you're seeing on the right here in orange is this gravitational wave plus redshift measurement for this one event. And what you see in the blue here is using the additional inclination angle, independent inclination angle that we received from the radio VLBI observations. We were actually able to improve this measurement by a factor of 2. What you're seeing in the underplotted green and orange lines are the 50 and 90% constraints of H0 back in 2018 that were coming from the CMB in the green originally, as well as on the right by using relative distance ladder measurements from the Cepheids and supernova 1As coming from the SHOES collaboration. And at the moment, between these two different sets of observations from the CMB as well as the relative distance ladder measurements, there exists about a 5.5 sigma tension. And so the hope is that gravitational waves, these bright standard sirens as well as dark standard sirens, may allow us actually an independent measure and to actually understand whether this tension is really a real tension or due to actual systematics in the complexity of making these measurements. And so in order to reach a 2% precision or so, we need about 50 of these bright objects, or indeed, if we have similar events to GW 170817 and the VLBI measurements, we need about 15. But this is a really rough order of magnitude number. But one big task facing the community is really to ensure that we can do this joint analysis as well as characterization of these different data sets, where there are many, many different parameters, as well as also different degeneracies between these different parameters, as well as actually the real challenge also in terms of modeling in order to do really this joint characterization as well as population analysis moving forward. So in the last part of my talk, I will just end with some perspectives. One question that I get asked quite a lot is, why have we not seen any more multi-messenger events? So what I'm showing here on the on this plot essentially is that after GW 170817, our one event constrained the merger rate by several orders of magnitude. Subsequently, as we have not seen any more, or we've seen one binary neutron star merger. In addition, we've seen that this rate has shifted and become much lower than originally anticipated, and this may have consequences for short gamma ray burst rates as well as our process elements. The second thing to stress is that our first binary neutron star merger that I'm showing on the left, it had a sky area of about 400 full moons and was our closest event so far. If we ask, why did we not see the second or the counterpart for our second binary neutron star merger seen in 2019, I'd like to really stress that it was only seen with one detector, one LIGO detector, and it had a sky error of a quarter of the sky, which you're seeing in these red patches, and the distance was 4 times the distance. It was much lower in signal to noise ratio. And what you're seeing on the very right are the best localized events that were seen in 2023, essentially when we only had 2 LIGO detectors. The Virgo detector was yet to come online. So really stressing the need to be able to triangulate. And this is why LIGO-India in particular is eagerly awaited to be really able to contribute here. And so the challenge has been the question of rate, the depth, how faint these objects may be as our gravitational wave detectors are improving in sensitivity, having significant target of opportunity time, as well as actually sending as accurate and precise gravitational wave alerts as possible. But of course, the opportunity is that we have new facilities also coming online with LIGO India, but as well on the time domain side. And so some of these that I'm showing is we have ZTF now operating with a field of view of 47 square degrees. And on already, as of last week, Rubin has been sending out, tens of thousands of alerts, yes, in the optical, as well as eagerly awaiting the square kilometer array. How many minutes? Can I have 4 minutes?
Yes, sure. Please go ahead.
Thank you. Sorry. And then, let me go here. And then we also have several new opportunities, new facilities on the UV in particular, the UVEX, as well as the UltraSet mission that I'm associated with a field of view of 210 square degrees, as well as new astroparticle facilities coming online. But where are we going also in the future? And so here I'd just like to spend my last 4 or 5 minutes, sorry, on the where we're going in the future in terms of multi-messenger astronomy. So what you're seeing in this plot here, you saw previously the strain noise as a function of frequency. And the orange line here is denoting the sensitivity reached with the current LIGO detectors. And you can see where we plan to go by the end of the decade, also with LIGO India in yellow, a factor of 2 sensitivity improvement, A sharp possibly, another factor of 2 sensitivity improvement, as well as with the next generation gravitational wave detectors, Cosmic Explorer, in green, as well as Einstein Telescope, a European-based project that I'm very busy working on at the moment, where you see this 10 times improved sensitivity in broadband, as well as shifting the seismic wall to lower frequencies. So it's both increasing the width, the depth, as well as the width of this bucket, which is really making these new detectors just so phenomenal and so exciting in terms of what we will be able to do. They will allow us to have unprecedented signal to noise ratio of our highest signal to noise, unprecedented measurements of our highest signal to noise ratio measurements. They'll also allow us to see different epochs of our low mass binary neutron star mergers. We'll be able to see the merger and the post merger, as well as the in spiral for our heavier binary black holes, discovery of intermediate mass black holes, as well as the sheer number. So we're really talking about an equivalent to an order of magnitude increase in the diameter of a telescope. And so I'll just end by mentioning the Einstein Telescope, which is a mainly European-led project. It was envisioned originally to be a single observatory with 3 nested interferometers in a triangular configuration 200 meters underground, separated the interferometers with 3 10-kilometer long tunnels, and the facility is aimed to last for 50 years and with a 10 times better design sensitivity. So that means 10 cubed in terms of rate of these kind of events. And there are several sites at the moment that have been proposed, one in Sardinia in Italy, one in straddling the Netherlands, Belgium, and the western part of Germany, and as well as one in Saxony in the eastern part of Germany. And some discussion still in the next 2 years will be about whether it will go for a triangular configuration, as well as the possibility of having 2 L-shaped detectors. So this is still an open question. But in that light, I would also like to mention that this new German Center of Astrophysics that I have recently joined in the last year, which is an initiative of the German astronomical and astroparticle communities, where one of the 3 pillars that are spanning astronomy, instrument, and data-intensive computing, one of the research focuses of the science aspect is to focus on supporting Einstein Telescope, irrespective of where the site is, And this new institute, this new center, aims to have about 1,000 people within the next 8 years. And we're currently located at the German-Polish border in Gorlitz. So I'd really like to stress a big welcome to any of you who would like to visit. Please get in touch, as well as the fact that also, I think even today, I'll be posting 5 job adverts for postdocs as well as PhD students. So please do look out, because we would love to have a diverse as well as very energetic group of researchers join this endeavor. And so I will end there in the matter of time, because I won't have I'm running out of time, but really just to stress, in the era of Einstein telescope, compared to the few hundreds of objects that we have seen, we are looking at observing hundreds of thousands of binary neutron star mergers per year, as well as 100,000 binary black hole mergers per year. And so I often joke that aside from my 2-year-old still keeping me awake, this is really keeping me awake. But in terms of real excitement, it's a real pleasure to be able to think about this. And then, of course, we have space-based missions, which will be also contributing to our understanding of our black hole distribution in the future. So I will end here just mentioning that if you're interested in the science or case of Einstein telescope, last year we put on the archive the Einstein Telescope Blue Book that really spans a treasure trove of topics in astrophysics and fundamental physics as well as cosmology. And really just to end by saying that I have really focused on the high frequency end of the entire gravitational wave spectrum that spans decades of frequency space. But of course, multi-messenger astronomy will span also the sources that are being emitted from this huge range. And of course, really exciting, as you heard yesterday, results coming from pulsar timing arrays, our understanding of supermassive black holes, as well as CMB experiments, as well as the future space-based LISA mission, which is focusing on the millihertz regime, where we expect to see electromagnetic counterparts also from these sources. So the future is both loud and bright. And I'm just going to end with just showing some of the strategies and advice I aspire to, particularly for this audience, but perhaps the most important thing I can stress is the ones where be confident in your choices and also embrace who you are. Yes, I think that for me, those are the main things just to stress. If you love doing science, if you love astrophysics, if you love having fun and you enjoy that, keep that dear to yourself, despite the challenges that will come and the bends and curves potentially in your career. Okay, thank you very much.
Thank you, Samaya.
Thank you.
That was a very inspiring and exciting talk. Anuradha, do you want to read out the
Yes,
questions?
I can just read out one question. Please write your questions in the chat if you have some questions about Samaya's talk. So this is one question from Mudita Sonavane. She's saying that, are there any observations, research on these events that link radio waves and gravitational waves?
Sorry, I'm muted. Yes, absolutely. So actually, as I'm on this slide, I should really just mention the efforts in pulsar timing arrays, which are really radio observations where we're essentially using neutron stars across our galaxy as a gravitational wave detector to observe nanohertz emission from supermassive black holes. So there's a real aspect in terms of radio observations. But then for these binary neutron star mergers, let me come to this plot here of Kunal. Yes, we actually did observe, and I was part of the team that observed the radio detection actually of at 16 days after the event. And this radio detection from this binary neutron star merger was essentially coming from the synchrotron emission from the blast wave as the short gamma ray burst jet actually hit the circumburst medium. And so as a result, there was the synchrotron emission that was observed, and this resulted in this X-ray and radio detection first at 16 days that is actually still being monitored very carefully. And of course, now we have seen hints that actually there is emission coming from the afterglow of the actual kilonova itself, not just from the relativistic jet. And one thing just to stress is that all of the observations that we saw followed after the gravitational wave merger, but in the case of the next generation detectors such as Einstein Telescope and Cosmic Explorer, because the frequency bucket of that sensitivity curve is actually much wider, we will actually have pre-merger information on the hours beforehand. And the hope is actually to see the prompt radio emission from these mergers as the actual system merges, with some delay time for the radio waves to reach us. But that really is one of the exciting things, and to localize the source pretty much immediately. So this is really one of the, I think, most exciting things in terms of multi-messenger coming forward with Einstein Telescope. I hope that answered your question.
Yes, it does. Thank you so much, Samaya. Please write your questions here, and if Samaya is around, she will be able to answer them. But in the interest of time, we should move on to the next speaker. Thank you so much, Samaya, for this wonderful and very motivating talk, and thank you for being part of the symposium.
My pleasure. Yeah, please also don't hesitate to ask questions also about personal life and stuff, because I had many questions also when I was a student, so please do feel free to reach out. Thank you. Happy International Women's Day.
Thank you. All right, so let's move on to our next speaker. So we have with us Professor Surabhi Sachdev. She's from Georgia Tech University in the US. So Surabhi, are you able to share your screen?
Okay. Are people able to see my screen?
Yeah, we can see your screen.
Hi everyone, I'm Surabhi. Thanks for inviting me to give this talk. I'm an assistant professor at Georgia Tech. Happy International Women's Day to everyone here. I'll also say that I'm a new mom with a 6-month-old at home, and we didn't really have childcare this week. So I'm a little sleep deprived and less prepared than I'd usually be. But hopefully we'll talk about new discoveries and methods for data analysis for ground-based detectors. Okay, so what gravitational waves have we observed? I won't spend too much time on this plot since Samaya already went over it, but we're basically filling the landscape of the stellar graveyard. So LIGO-Virgo-Kagra detectors are sensitive to neutron stars and black holes, and really the only kind of signals we've observed are binaries and the last few cycles before they merge. So each observation here from LVK includes 3 points, the 2 components that are in spiraling, and then the remnant that they produce. Most of what we've seen are binary black holes, but we've also seen a couple of binary neutron stars and a handful of neutron star black holes. So I'll be focusing on the latest detections. We recently released our latest catalog, GWTC4. This included 218 total candidates with p-astro, which is the probability of astrophysical origin as opposed to a terrestrial origin greater than half. Out of these, 128 were new. So these were candidates that weren't previously unknown that we discovered in GWTC4. Out of these 128, 86 were highly significant. They had a false alarm rate of less than 1 per year. And we basically doubled our catalog size in comparison to GWTC3, which was our previous catalog. Here, I'm just showing you all of the events that are in GWTC4. And what I'm showing is the total mass and effective in spiral spin. So the two things that we measure really well of our candidate events. So let's talk about some of the interesting events in this catalog. First step is GW 230529, and the name here is basically the date in which we discovered them. This is likely a neutron star black hole system, and this one was really interesting because of the mass of the black hole, which lies in this mass gap region between where we know that the neutron stars to exist and the black holes to exist. So this is this ambiguous region where we're unsure whether the component is a neutron star or a black hole, though in this case it's most likely a black hole. So here what I'm showing is that we're looking at the mass spectrum of black holes in neutron star black hole binaries. And previous to 230529, the minimum mass of a black hole in an NSB8 system was 6 solar mass, and now it has reduced to around 3.5 solar mass. And this is important because when you have a neutron star black hole system, if the black hole is much heavier compared to the neutron star, when it merges, the black hole will eat the neutron star whole and you won't see any electromagnetic counterpart. So all of the exciting science that Samaya just talked about, we wouldn't be able to get that. But if the black hole has a mass that is comparable to the neutron star, then it will tidally disrupt the neutron star and you could have some electromagnetic counterpart. Although in this case, we did not detect anything. So we're very excited about this event because it increases the likelihood of having neutron star black holes that are EM bright. Let's move on to another interesting event, 230814. This was the loudest event in our GWTC4 catalog, but it was only detected in the Livingston detector. It's a very vanilla binary black hole in the sense that its masses are very similar to most of the black holes that we see, but it's interesting in some other sense. So we're looking at the waveform reconstruction for this event using a couple different waveform models. And the thing to note is in the ring down part, the non-GR waveform is more compatible with the data compared to the GR waveform. So there are some signs of deviations from general relativity that we're seeing in this event, but only in the ring down. The inspiral part is very consistent with general relativity. Now, we're not saying the GR has been violated, and in the paper, we actually explore many possible explanations for these deviations. And the two most likely ones are that we don't actually have very accurate gravitational waveforms for this region. And the other one, which is also a very likely explanation because we only have data from one detector, we cannot rule out just noise fluctuations causing this deviation. Nevertheless, an exciting event. Let's move on to our next event, GW231123. This is the most massive event in this catalog, with the primary being already greater than 100 solar mass and the total mass of the system being greater than 200 solar mass. In comparison, we're showing our previous most massive event here, which was the GW190521 event from our previous catalog. Another interesting thing about this event is that both black holes in this binary are maximally spinning. So also very interesting. And combined together, the fact that the black holes are highly spinning and that the secondary is also likely in what is known as the pulsational instability supernova mass gap, this could hint towards hierarchical merger origins for this binary black hole system. So the next one here is a pair of events, 241011, 241110. The names are confusing. These events are actually not from our GWTC4 catalog, but are part of the data that is beyond GWTC4. So this data set as a whole, we're still analyzing, but we've released some events from this data set. And the reason these events are grouped together are because the properties are somewhat similar. So both binary black holes have their primary mass. So the component that is heavier, the spin is aligned with the orbital angular momentum and quite high. So around 0.6 for our 24-10-11 system, and around negative 0.5 for our 24-11-10 system. And the other interesting thing is that both of the systems have very asymmetric masses. So the primary is around 15 to 20 solar mass, while the secondary is around 5 to 10 solar mass region. And again, taken together, the fact that the masses are asymmetric and the spin of the primary is around 0.6, 0.7, this hints towards hierarchical origin scenario. Now, the gravitational wave data cannot by itself tell us how these events are formed, but their properties hint towards hierarchical merger scenario. There are a few other things that we can do with these events. So 24-10-11, besides being interesting because of the spin, was also very loud. So it provides us the best measurement of spin-induced quadrupole moment, and we're able to test general relativity that way. So here we're just showing some possible scenarios in which the primary of these two systems could have formed from merger of previous binaries. In addition, 24-10-11 allowed us to measure relative amplitudes of higher order modes, and both binaries as a whole rule out the existence of novel boson particles with masses in some range. This is because if these boson particles existed, they would have taken the spin away from this binary, and we wouldn't have been able to measure such high spins. So a lot of exciting science that we can do with these binaries. Let's move on to our next exciting event, 25-01-14. Again, this part of the data we haven't released as a whole, but we have released data around this event. So this is not part of the GWDC4 catalog. This is the loudest event that we have detected so far. This was basically a 15-09-14. So our first binary black hole detection, basically a duplicate, but 3 times as loud. And I should mention that the reason it was 3 times as loud is not because it was much closer to us, but because our detectors actually got much more sensitive compared to 01. So it was basically a 15-09-14 that we were looking at with more advanced detectors. And so we were able to measure it extremely, extremely well. So here you're seeing the actual whitened data, which looks basically like the reconstruction waveform. So there's very little noise here. Now, because it's so loud, we were able to actually test Hawking's area law. So there is Hawking-Bekenstein area law, which basically says that the area of the black hole encodes entropy. And since entropy can only increase with time, this actually implies that the area of the black hole can only grow. Now, the reason we're needing a very high signal to noise ratio to be able to test this is we want to be able to measure 2 parts of the waveform independently. So we measure the in-spiral independent of the ring down. And what we can do is when we measure the in-spiral independently, we can infer the initial masses and spins of the black holes, which allows us to measure the total initial area. And then when we measure the ring down independently, we can again infer the final mass and the final spin of the black hole and measure the final area. And what we see is that the area has grown to a very, very high confidence. So the reason we want to do this measurement independently is because away from merger, we can assume GR to be true. So there is some assumption that we do need to make in order to be able to perform this test. All right, that was a very fast review of latest exciting events. Now let's talk about populations as a whole. So our latest catalog, as I mentioned, has hundreds of events, and using a subset of those hundreds of events, so I think this includes a set of around 150 events based on some false alarm rate cut, we're able to measure the population of our binary black holes. I'm only going to focus on binary black holes because we don't have that many neutron star containing events, so the population there is still a bit ambiguous. So we're looking at the population distribution of the primer here. So the heavier of the two black holes in a binary black hole system. And I'm going to draw your eye to the broken power law plus 2 peak, which describes our population in GWTC4 extremely well. So the broken power law is a good approximation with 2 peaks, one around 10 and one around 35 solar mass. And I'll note that these existed in our previous catalog too, but now remain. So in comparison to GWTC3, you'll note that the uncertainties have shrunk, so we're more confident in our population measurement. And the last thing that I'll note is a more kind of independent model that doesn't, force you to have 2 peaks is actually recovering an extra peak around 20 solar mass. So this is all still a mystery to us. We don't know where these peaks come from in astrophysics sense. What is the reason that the black hole spectrum has these peaks? And that's something that's still being studied. Though there is, there's some potential reasons for having this peak. For example, because of the pulsational instability supernova mass gap at this that's beyond 60 that forces black holes to form at this below the mass gap region, but that alone cannot really explain this peak. So it's still an active research subject. In addition to studying the binary black hole mass spectrum, we can also infer the rates of our binary neutron star black hole, and binary black hole systems. And you'll notice that the rates in binary neutron star black holes are still quite uncertain because we haven't really seen many of these. But for binary black holes, we're really starting to constrain the rates. So we know the rate really, really well. And finally, the nice thing with GWTC4, which we saw the hints already in our previous catalog, is that we can measure the rate as a function of redshift, and we can clearly see that there is a trend that it's increasing with the redshift, so following some arbitrary star formation rate. Okay, so with that quick review of our results, let's focus on how do we detect these things. So we have various search pipelines that are operating twice, actually, once in low latency to be able to alert astronomers and enable multi-messenger astronomy, and then offline, which makes use of better data quality, better background, and better calibration. So we run all of these pipelines twice, and there is 3 main kinds of pipelines. One is model search pipelines that are looking explicitly for compact objects from all sky. And then there is unmodeled search pipelines that don't make any assumptions about the signal model. Again, they're looking for signals from all sky. And then there is multi-messenger pipelines that are targeting a particular region in sky that's given by some external electromagnetic or neutrino event. So now I'll focus on the model search pipelines that detect the compact binaries for the rest of this talk. The main principle that our model search pipelines use is known as match filtering, which is able to extract signals as long as you know what your signal looks like. So here I'm showing the basic principle behind match filtering. Blue is our template of our signal. Black is our data, which also contains signal, but you can't really see where the signal is. So you take your template, you slide it across your data, and you study the cross correlation at each time slide. And the result here is shown in red. And when the template here matches the signal hidden in the data, you see a peak in the match filter output. And that's the basic principle behind our search pipelines. Now, an important caveat here is that we need to know what the signal is that we're searching for. Fortunately, compact binaries are extremely well modeled, and the in-spiral merger and ring down of these systems are modeled using various different techniques. But we also don't know what the parameters of these signals a priori look like. So these are extremely well modeled, but these models have various parameters. So in a purely GR, not including matter effects, I can take my compact binary system and roughly have 15 parameters. I can group them into intrinsic versus extrinsic parameters. Intrinsic will depend on the object, on the source itself, so masses and the 6 spins, so the 2 3-dimensional spins. And the extrinsic parameters depend upon where the source is located with respect to the observer. So the sky location, distance, for example. Now, if you make certain assumptions, such as that the system only emits the most dominant 2-2 mode, and that the 2 spins are aligned with the orbital angular momentum, in that case, we can actually simplify this problem quite a lot. So most of these extrinsic parameters can then be absorbed as an overall amplitude term, besides the phase and the time of coalescence, which we can maximize over analytically. So if we make this assumption, we, instead of this 15-dimensional problem, have a 4-dimensional problem, which is only restricted to the intrinsic parameters, so the 2 masses and the 2 spins. And that's what our flagship searches do. So we just simplify our problem, and then in the intrinsic parameter space, we lay out a grid of templates that we can then filter over for our entire data set. Now, if noise were stationary and Gaussian, this would be the end of the story. I have my template bank, I filter it against my data, I'm producing SNRs, and I just rank my events based on the signal to noise ratio and call it done. Unfortunately, noise is not Gaussian, and so we actually have to do a lot more to be able to detect our signals. In particular, all of our pipelines use some kind of signal-based vetoes, which we're able to discard many of the most annoying glitches, and other factors like time delay and phase delay between, if you have multiple detector output, that we can use to better inform our ranking statistic. So here I'm just showing the likelihood ratio, which is a ranking statistic we use in one of our flagship searches known as GSD-Log. I'm not going to go into the details here, but if anyone has questions, we can talk about it afterwards. So once we have a ranking statistic, what we can do is we take our candidates and we assign ranking statistic to each of them. And then we can rank them against one another. But we still don't know in absolute terms how significant an event is. And so what we need to do is to go from our detection statistic, which in this case is log likelihood ratio, to something that is more intuitive, such as a false alarm rate. And different pipelines do it differently, but the most common way that is perhaps intuitive to you all is doing time slides. So we take the output of our 2 detector output, and we perform time slides to just create a lot of background. And then we can, in this background, we have a lot of noise candidates. We can assign them the same likelihood ratio. And we basically can get the distribution of the likelihood ratio or a ranking statistic, what it looks like for noise. Once we have that, we can assign a false alarm rate to each likelihood ratio. So this is the noise model here. We're looking at the noise distribution for our ranking statistic. And then we can plot what our foreground looks like. So this is the result from GWTC1. I'm showing this because we have a limited number of signals, so it's actually easier to see. So in the bulk of our observations, we're going to match the noise model really well, and that is what we expect because most of our candidates are actually noise. But what you should see if you contain signals is this tail that rises above our background model. And this is where all of our events are. So 170817, the event that Samaya was describing, was our loudest event in GWTC1. So what was new in 04? Now 04 has already ended, so it's not so new anymore, but these were some of the developments compared to our previous observing runs. We were actually issuing early warning alerts. So unfortunately, we did not have a very loud binary neutron star in 04, but we were ready in case another 170817 happens. We should have in principle be able to send out an alert before merger. So the idea is that binary neutron stars or neutron star black holes last a few minutes in our detector's band. So if they're allowed, which 17017 had a network SNR of about 32, and already a minute before merger, the network SNR was 11. So the idea is that you keep accumulating SNR, and if it's loud enough, you should be able to detect it before merger. And so this is from a simulated study that we've performed. These are the final signal to noise ratios of some binary neutron stars and the distances. This is assuming final design sensitivity. And you can see for something that has a final SNR of 11, we're able to detect it 15 seconds before merger. And of course, the sky localization is not so great, but it gets better and better as we get to merger. And so the louder system is, the more earlier we're able to detect it. Here we're gonna look at how the sky localizations evolve with time. So these are the same systems that I presented in the previous slide. And so when you first have the detection, the sky localization is quite large, but as you contain more and more, you obtain more and more signal, you start to hone in on the sky location. And so the idea is that if we produce these alerts early, the astronomers can already point in the general location of the event and hopefully not have to slew as much afterwards. Another new thing we were doing in '04 was issuing low significance public alerts. So not just the very significant events, but events that were at a false alarm rate of 2 per day. And the idea being that we can cross correlate these with external low significance or high significance events. And if they happen to coincide in time and sky location, they can we can discover some multi-messenger events that way. A lot of work was done to improve our latency of the alerts to actually make sense of the early warning pipelines. So in our previous run observing 3, the best we were able to do was a few minutes. It took us a few minutes to be able to send out the alerts. While in '04, we were sending out alerts at around 30 seconds. And this was work that we had done before '04 in preparation for these early warning pipelines. And so now what you will see is actually data from '04, where we consistently released our alerts at about 30 seconds. Another new thing we were doing was sending out alerts for subsolar mass systems. So previous LVK had performed these searches only offline. And the search basically looks for compact binaries where at least one of the components has a mass less than 1 solar mass. And the reason we're doing this is because one reason is that even though we don't think there is compact objects there being produced astrophysically, so no neutron stars or black holes that we would typically think of, they could contain primordial black holes or black holes being formed from some exotic mechanism. The other reason we're looking for these is that we don't actually know where the boundary, the low mass boundary for a neutron star is. It's thought to be around 1 solar mass, but no one's actually measured it. So it's possible that there is neutron stars that exist at the boundary around 1 solar mass. And so by looking for these in low latency, we're actually happy if astronomers follow these up and we can get some more data point in case there is an electromagnetic counterpart. And we actually did have some exciting subsolar mass alerts in '04, which were also followed up. And for a moment there was like this counterpart that we thought could be exciting, but is now believed to be a supernova. I'm not going to go into more details about it in the rest of time, as I see I'm already over the time. But this is just showing that we don't have all of our results out yet. So the 218 events in our catalog contain data up to '04A, '04B, and '04C. We're still analyzing, but from the online searches, we know there have been more than hundreds of events there that were highly significant. Now, I've talked about a lot of science, and to achieve these, we actually need our detectors to be sensitive, right? So one of the ways we measure the sensitivity is the average sensitive distance that we're sensitive to a binary neutron star. And here I'm just comparing the sensitivities between O3 and O4. And there was about a 25% increase in the sensitivity, which leads to about a twice increase in detection rate. And where are we in the observing timelines? We had a big gap between O3 and O4, mostly due to COVID. And then we had a very, very long observing run that, some of us joke this is the run that never ends. We're on a break now, but not for long. We're actually going to be observing again later this year. We're calling it IR1. The plans for O5 are currently unclear, but we'll definitely have more data later this year. So stay tuned for results from the second and the third part of O4B, and also for our new run IR1, which is about to start in fall. I'll leave my conclusions here and stop. So if people have questions, I'm happy to answer.
Yeah, thank you so much, Surabhi, for this wonderful talk and very informative and a nice summary for O4A events. So we have some questions in the chat. So in the interest of time, we'll take one question. So I'm going to read that to you. Mudita is asking, how is the sensitivity, efficiency of these pipeline estimated if there are deviations? And the second question is, how is the efficiency of early warning pipeline is estimated?
A very good question. So I actually don't have slides to show you that, but the way we estimate efficiency is by performing what we call as injections. So these are simulated signals that we inject in our data, and we do hundreds of thousands of these. And so besides looking at real data, we're also looking at these simulated signals, and we compute false alarm rates for each of these simulated signals. And that tells us how good we are at detecting the signals, and we calculate efficiency, which is in terms of VT, so the sensitive volume that we're sensitive to, and time being the time that we're observing for. I don't know if that answers your question, or and the same thing is true for early warning pipelines as well. So we're simulating a lot of injections and looking at how well we can recover them and how far in advance we can recover these.
Yeah. Thank you, Surabhi. And if people have questions for Surabhi, please write to them. And if Surabhi is around, she might be able to answer them. So thank you so much for your time, Surabhi. I know you're very busy and very tired, but it was a pleasure to having you here. So
thanks,
over to
Anuradha.
you.
Thanks for inviting me.
Thanks a lot, Surabhi. So we heard a lot about searches and data analysis. So now we will move on to numerical simulations. And we have with us Professor Manuela Campanelli. She's from Rochester Institute of Technology in the US. And she will tell us about numerical simulations of binary black hole mergers. So we can see your screen, Manuela.
Do you hear me?
I can hear you, yeah.
Okay. Let's see. You should see me too now.
Yes, I'm going to spotlight you.
Okay, perfect. Let's see. Do you see the slides again?
Yes, we can see the slides.
Perfect. Okay, thank you very much for having me at this interesting conference. It's a pleasure to meet you all. My topic is going to be slightly different from what you have heard from the previous talk and probably from most of the talks in this conference, which is very focused on gravitational waves. I'm going to be talking mostly about simulations of supermassive binary black holes, and I'm going to be talking about them as counterpart to gravitational waves. So it's related somewhat indirectly to gravitational waves, but we are going to be talking about something that is coming not so much by the space-time dynamics, but mostly by the light generated by the gas that surround these systems. So let me see. Okay, so well, I think you have seen this plot many, many times. It's not surprising that we're seeing many binary black holes. This was already, in fact, predicted and noticed, by Kip many, many years ago, that these would be the most loud systems in the universe. So seeing them is not surprising because they are louder and they are pretty much everywhere. We do have obviously wonderful signals today. This is just the last famous paper about the detections, and it's impressive how well we can actually determine that this is actually now a black hole. So what I'm going to be talking about is not so much about gravitational wave signals, as I said, but I'm going to be talking about counterparts to gravitational waves. The reason is because binary black holes are really spanning the entire gravitational wave spectrum. We see that they're very peculiar in terms of sources. There's no other source actually in the universe that spans such a large spectra. And the ones I'm going to be talking today about is the ones that enters into the LISA band, but also in the PTA bands. So we're talking about 10 to the 6 solar masses black holes and up to 10 to the 9 solar mass black hole here. So we know that there might be such black holes. We do have, in fact, and we have probably heard already from the talks of nanograv speakers in this conference that there might be supermassive black holes, many of them in the universe, as this is most probable signal coming from the stochastic background signal detected by nanograv. LISA, as we know, is now determined to be launched. It's already an ESA mission, and it's going to go up around 2035. So this is already a good time for us to start doing interesting astrophysics concerning supermassive binary black hole merger, in spiral merger, and so therefore look at electromagnetic signature. So why should we look for electromagnetic signature from this system? Well, we know that binary black holes should form because galaxies do merge, and this happens usually at 100 kiloparsecs away, where the galaxies are really very separated among each other. So it takes quite a lot of time, almost close to Hubble time, to actually for the black holes to merge. But there are processes that allows the black holes to get closer to each other, such as dynamical friction, torque from gas, and other processes that tends to reduce this separation among the supermassive black holes to the very small separations that we're talking about for gravitational wave emission, which is, a small fractional parsec. Actually, we're talking about astronomical units here. So once they are in this regime, obviously, there is a lot of gravitational waves that are emitted. And so these sources become fairly interesting, not just from the point of view of gravitational waves. And they become, obviously, from the gravitational point of view, also sources for LISA and PTA. But they also emit, as I said, light, because there is a lot of gas around. And if this gas is heated by any processes, either accretion or shocks that happen close to the black holes, then it would emit some luminosity. And one can actually make a rough estimate even before doing the simulations by using bone the accretion around the system. And you can get, this type of luminosity that, will be gathered, for this in terms of adding on luminosity. So you can see that it depends on the mass, obviously, but they become fairly luminous in the universe. So it makes sense then, therefore, to ask the question, are they really detectable? And so from the point of view of light, and that's a fairly complicated question, because unlike gravitational waves, which are simple in terms of they're just so yes, of course, I say it's simple, but they depends on obviously the parameters of the binary, the mass, the spins, and all the parameters, the orbital dynamics, and so on. But here there is a lot of other processes that intervenes when we talk about light, and so things become really, really complicated. We do not actually know what to look for. So we don't really know what kind of signal they should be emitted. And obviously, the signal that is emitted by light depends on the environment close to these black holes. So if you look at the actual detection, there are numerous of them, but they're of the order of hundreds. They're not many, as one would expect. And typically what you see dual AGN. You have most of these signals coming from dual AGN. Here's examples. You can see them very, very far from the universe. In this case, is a binary quasar, really located very far in the universe. But it's still, in the kiloparsec, the black holes are still kiloparsec separated. You can see them also in the very local universe. So you can see the double nuclei. You can see double nuclei also look in the radio. So this is VLBI observation. You have many years where you see or you follow a binary for many years, and you can see the two nuclei going around here. And then interesting, you can also see signal in the light curves, which are attributed to self-lensing. And we're going to be talking a little bit later in the talk about self-lensing. But there are features due to the fact that the light is distorted by one of the black hole passing behind the other one. So there are candidates out here. There are many candidates. People are looking for things like periodic signatures, especially. And it's always very, very difficult to interpret this periodic signature because there are many things in that can actually produce periodic signature. And one is, for example, red noise. So one has to be very, very careful about red noise in this when we do this kind of observation of periodic signals. But there are cases, and especially in the case of blazars, where one can see very clearly the cycles that are not actually due to red noise. So you can see these periodic features. These are specific to a specific blazar that has been observed for a number of years, where you can see these very, very clear periodic signals, which indicate that maybe this is caused by a binary supermassive black hole. So just so for those of you who are not so much in astrophysics, right, blazars are like quasars. They're just pointing their jets are just pointing toward us, right? So so we can therefore we do have ideas that there might be binaries there, and there might be signals. We just don't know exactly what type of signal they would produce. So we have to model them. The fact that we have to model them is also been pretty evident back in the past when we were looking for this recoiling black hole. Now in 2007 or 2007, there were a flurry of papers. I started publishing papers also during these years about the presence of recoiling black holes that occur during the merger and after the merger of two supermassive black holes, but any black holes that would essentially merge could produce recoils if the black holes have spins that are not aligned, particularly aligned with the orbital momentum, or have unequal masses. And the fact is that if this happened, then the recoil could be large enough, then the escape velocity of the galaxy is, and that means that the black hole will get ejected from the galaxy and carry on some accretion disk along that would be luminous long enough to be detectable. So this was fairly looked at upon by astronomers many, many years ago. Still today, they were looking for this type of recoiling black holes, and they were looking from a variety of possible signatures because, again, we didn't have simulations that predicted what type of light signature would be emitted from these systems. So they looked at double peak emitters, offset galaxy nuclei, population of galaxy without supermassive black holes, X-ray afterglow, feedback trace, a lot of potential signatures. Like for example here, where they looked at velocity shift from narrow lines, again, could be interpreted that this velocity shift could be due to essentially a recoiling black hole. And then perhaps the easiest way to detect a recoiling black hole was to actually look at the displaced black hole from the actual galactic center. So if you're able to estimate very well the galactic center, then you can look for a luminous spot here that is displaced from the galactic center. This is the most recent famous recoiling black hole, perhaps one of the strongest case, 3C186, which is pretty recent. As you can see, there have been papers up to very recent years about this case. And so one could look at these things. But again, it's not very, very clear unless we do have specific light curves or spectra coming up from simulations to identify this system. So I think I said it's fairly complicated. So we really need theoretical models to be able to distinguish these systems. The problem is that it is challenging. It's very challenging because supermassive binary black holes, come from, mergers of galaxies. And we know that hierarchical galactic assembly model predict a large population of these binary AGN. So we know they're there across all cosmic epoch. The models, though, that we need to construct, so therefore it needs to be able to connect with this earlier cosmological simulation down to the scales of subparsecs. So it's therefore very important in this field that this gap is actually closed, that essentially we are able to connect from cosmological simulation down to the very small simulations, small scale simulation that we are doing. And we're talking about very small separation here. Now, in my talk, I'm going to be focusing on this particular small separation scale because I'm very interested in producing counterparts of gravitational waves. So when we want to simulate the scenario of very close separations, there are many things that we need to consider, not only the astrophysical flow scenarios that I just said depends on details of the prior history of the binary supermassive black holes. But obviously there is also a wide parameter space. We do not know what mass ratio, what separation, what eccentricity and spins. And so we have to include that. And that's typical also for gravitational wave signals that we have to include these parameters. But in addition to that, now we do have fluid parameters. So we have to consider what type of accretion rate is there? Is there any viscosity, magnetic field, obviously, disk scale height? What's the type of the disk? Is there a disk or is not a disk there? Or is it just a very tenuous gas? So there is just magnetic fields in a very, like in the Sagittarius A's that are very, very strong, but very, very thin disks. So there's many unknown concerning, obviously, the state of the fluid close to the binary. So we have to be able to simulate a variety of them. And then we also have to be careful about how we model our so-called heating and cooling balance. So in other words, we have to be able to describe the radiation transport of the photons in a very well manner. So, and that requires that we do full radiation transfer in order to model this. So people assume usually different type of model here. You can get, radiatively inefficient gas cloud or a radiatively efficient circumbinary disk. In the simulation that I will present here, I'm going to be talking about mostly radiatively efficient circumbinary disks. So there is radiation transport that is actually cooling the disk around the supermassive black holes. Then we do also need, obviously, general relativity, because we're talking about the very small separation scales where relativity start to play a role. We need GRMHD, which stands for General Relativistic Magnetohydrodynamics. And we need to do this at a very accurate level. So it's not just the accuracy of the space-time that we care here about, but mostly we do care the accuracy of the gas dynamics. So that means that we have to resolve the magnetorotational instability, which is what drives accretion in the circumbinary disk to the binary. We have to resolve turbulence. And then we have to have realistic thermodynamics, plasma physics, and radiation transport. And these are making things fairly complex, because now you have the Einstein's equation couples to actually the equations that describe how matters behave here. And obviously we have equational states, and we have the Maxwell's equations, and then we have the equations that describe radiative losses. And for radiative losses, we're going to see there are various models that one can do, which are more or less accurate. But if you want to do full radiation transport, then you have to solve the Boltzmann's equations. So this is a system that is computationally expensive, because not only is just that it's complicated from the point of view of the equations, but you have to start the simulation from very wide separations. And then there is binary separation, and there is a wide range of dynamical scales involved, because you have to make sure that whatever initial condition you consider around the binary supermassive black holes, the gas has to reach what is called the quasi-steady state of quasi-steady state, essentially. So it means that if you look at the dynamical scales involved, then the dynamical scales equilibrating the gas, quasi-steady state of accretion, it's much longer, for example, than the gravitational wave dynamical scale. So you have to therefore simulate these things until you reach this quasi-steady state. So many years ago, I started this program to actually do that, to simulate binary black holes embedded in a circumbinary disks. In general, we took a circumbinary disk that was, like in here, more as a tori. I can try to run a simulation here, distributed matter, and then we let it equilibrate for many hundreds of orbits. And that, until it actually produce the turbulence that we expect in the system, until we have the disk that reach what is called the steady state of accretion. You can see here, for example, the accretion rate into the binary, and you see that initially the disk is not equilibrated. The accretion rate, is oscillating a lot, so it's starting to establish here the MRI and the turbulence. You see that the disk is actually going at around these states where it's establishing this turbulence, and then it starts to relax later on. It will relax, and then it will eventually reach what is called the steady state of accretion, which is pretty much, constant. Yeah, there are oscillation, obviously, because there is a binary here, but you can see that, the trend tends to be stable. So that is when you can start believing your simulation becoming astrophysically relevant. So that implies, as I said, doing many, many orbits. Typically, over 200 orbits, 250 orbits, depending on the system, depending on whether you have equal mass, you have spins, etc. But the order is of hundreds of orbits. And the thing that we found already many years ago was that we found that there is a generic lump that develop in the within the circumbinary disk that has a certain frequency, characteristic frequency. That lump or overdensity seems to interact with the streams that falls into the binary and produce a characteristic signal. This was a work that we did many years ago, and it's still very relevant because we do have this lump here, and this lump, as I said, is an overdensity that generically form and interact with the black holes here. And every time it does this, it produces a signal, a light signature. But at that time, and I think I'm going to skip this because I won't have time. I might go back to this later on. Okay. At that time, we didn't reach merger. So in the most recent simulations that we've been working on now with several of my graduate students was to extend these simulations down to merger and to the post-merger. So what we did was, again, we took these accretion disks and equilibrated it. Now this movie will stop and you'll see it will run for over 200 orbits. So you can see here the extent of the disk. The white hole there that you see is actually, there is no simulation grid there. We have cutted it out. It's where the binary is. Why we did this is because you see the scale of the disk is much larger and we're running it to very, very long times. And what we are interested here is actually to equilibrate the circumbinary disk. So we're not interested in the so-called cavity. We call it cavity where the binary is, okay? But we simulate this for a very, very long time. And we do this actually using the post-Newtonian equation of motion for the binary spacetime because it's way in the inspired regime. We use also spherical coordinates because they are actually better for simulating accretion systems for a very long time, like in this case. So, and then when we reach a certain point, which is this point of the quasi-steady state of accretion, we do a handoff to another code that now is a numerical relativity code, and we place the grid back into this hole. And so what you see then, once you put the black hole back in here, is that the gas immediately accrete around around each of the black holes. They form these two mini disks. And then you see that the accretion actually happen in a very orderly fashion, at least for this particular system that I have in the system, in the screen. You see that there are streams here that are detached from the circumbinary disk, from the edge of the circumbinary disk, and goes into each of the black holes. And those are essentially what are responsible for forming these mini disks. And they do form very, very quickly. There is some gas that falls also in the so-called cavity, but sort of this cavity stay for a long time, we're going to see. It's not entirely a cavity, but the density of the gas here is much lower compared to the density of the gas around each of the black holes. So essentially, you have a system of a circumbinary disk, which has this lump, which I just told you. There are streams that falls into each of the black holes. And there is also an exchange here between the two mini disks. You see the gas flows from one of the mini disks and the other mini disk, and we call this sloshing. So it's a fairly coupled system. And so this can be done thanks to the fact that we are using different codes and different approach to simulate this system for a very, very long time. Let me remind you that this is, a lot of orbits as compared to what numerical activity typically do gravitational waveforms. We're talking here, more than 250 orbits plus another 50 orbits in the regime where we reach the merger. So we're talking over 300 orbits, binary orbits. So what we found, Okay, so what we found when we get to merger, and that's probably what you like to hear here, because I think it's been a mystery for a long time. There were simulations, obviously, that were done in 2D hydrodynamics, not in full relativity, where people made some assumptions about what happened close to the merger. But until we got there, we really actually didn't know. And so here's what we found. This is for a particular system where the black holes are not spinning, and this is close to merger. This is in the first plot, as you can see here. And you can see there are mini disks, but as soon as the binaries start to get very close to each other, and the mini disks will tend to shrink and disappear, just because the so-called Hill spheres that the mini disks need to occupy shrink very much, and there is no more room for accretion to happen around the black holes. And when they get very, very close, you see that the gas will tend to fall into the cavity. There is not such an orderly streams and mini disk anymore. It becomes fairly chaotic, and there are a lot of shocks. And finally, during the post-merger, you have keep to maintain this shocked region for quite a while, we're going to see. And that's fairly interesting because these shocks emit a lot of light. They produce a lot of heat and they emit a lot of light. And you can see this in the light curve. So initially you see that the light curve, drop because obviously initially you have most of the light coming from the mini disk here. But then as soon as it reaches merger, then the light curve shows that, eventually in a post-merger, it will jump up. And it will jump up for more than 50%. And most of the luminosity here, and if you can compare the curves here, you see that the dark blue is actually the regions very close to the binary. So and then the red one is actually the region farther from the binary, so coming from farther the disk. And you see that much of the components of the light is coming from the regions very close to the black holes. So it is produced essentially by these shocks that happen very close to the binary. So the big questions that we are trying to answer now is, what happened, therefore, not just to the light, but also to the jet. And what we can see, because these are two spinning black holes in these simulations here, this is the equatorial plane, and this is now the polar view. You see that there are two double jets coming out from these binary black holes. And once you reach the merger, the double jets will tend to essentially disappear because the mini disk gets shredded. And then finally, when the final black hole form, you have a single jet that reappears. So you have this interesting phenomenon, which we call a deep then jump luminosity features, not just of the thermal light coming from the accretion disk, but also from the synchrotron emissions that you have from the jets. So I think so here I think is more details about what happened in that particular simulation. I'm going to switch to talk now about what happened if you instead of assuming the spins align with the orbital angular momentum, which was the case I was presenting to you before, which is this case here. What happened when the spins are either counter-aligned or completely one align and one counter-align, and this case, and they're both counter-align, and this is non-spinning. These are simulations that are right now carried on by one of my graduate students, Maria Chiara De Simone, and you see that what she is finding here is that actually these mini disk really change completely structure depending on the direction of the spin. So they are really puffier and very well formed if the spins is aligned with the angular momentum, the total angular momentum, while there is almost no mini disk if they are counter-aligned. And correspondingly, you see that the jets, obviously, which are related to, and they are forming when you have spinning black holes, you see that the jets are also affected by the direction of the spin. This is work in progress. This simulation are now being carried down to the merger to see what happened on merger. But you can see that the dynamics is fairly affected by the spins. Oops. Okay. So another question that we might have is that what happened when the spins are not aligned at all, neither contra-aligned, not aligned. They have some directions that are either oblique or they have components, a large component of the spins that are in the orbital plane. So this is a case where you could have very large kicks. These are the three cases that people have been studying. In particular, the largest kicks come from the so-called super kick scenario, where you have the spins or a large component of the spins that is in the orbital plane, or the so-called hang gap kick, where the spins are at 45 degrees with respect to the orbital angular momentum here. These two cases produce kicks that are of the order of 1,000 kilometers per second. So they are particularly interesting from the point of view of astrophysics, obviously, as we said before, because they have implications for the formation history for galaxy formations and for also identification of binary remnant of binary supermassive black holes in the universe. So there are other phenomena that may happen when the spins are not aligned, except we have precession, obviously. So there are phenomena like one of the black holes can completely change directions of the spin, or there are other cases when you have, for example, a mass ratio that is at least out of the order of 1 to 10, where you have that the total angular momentum can reverse completely. So having therefore an implication also for the accretion. So we are currently looking at this scenario, and we started looking at the first case for this case of the both super kicks and hang gap kick. Again, this is work by Maria Chiara De Simone. And let me show you the first movie here. This is the case where this case here, the black hole start in this scenario, the spins are aligned in this direction. So, the jets are going in the directions of the spins, at least close in, right? Because of the Blamford-Zaniac phenomenon that is responsible for launching the jets around the spinning black hole. And now let me run again the simulation. This is a simulation is going on. You see that there are no mini disk in this case forming. You don't see even the jets. It's very chaotic here, because the jets, if they're jets, they are actually pointing in the direction of the circumbinary disk here. And so therefore they are hitting the gas, and therefore they are causing this very complex dynamics. There is gas here all over. There is a lot of shocks coming in from this region. We do expect that this shock region will be emitting a lot of light, but there is no particular mini disk or jets here that you can identify. In the case where we call the hang gap kick, where the spins are oblique, you can see that a similar situation arises, but now mini disks are still formed. You just don't see them here because they're very warped. And you also have jets. So in this particular case, and this movie can go very, very long because Maria Chiara was able to run this up to the post-merger and obtain a kick. So we will let it going for a little bit, but I don't know, my time is limited. Since it's a very long simulation, I'll show you directly the results that Chico obtains. So as I said, in this case, the spins are around 45 degrees with respect to the orbital angular momentum here. She finds that the mini disks are extremely warped. As you can see, the mini disks around the black holes are extremely warped. There are jets, and the jets, and you can see this is the magnetic field lines around the binary. And you can see that the jets are essentially following the direction of the spins here initially, at least very close to the black holes, but then they realign with the orbital angular momentum. You can follow this simulation pretty much up to merger. And what you see is that you see a recoiling black holes at the end, and you can see it moving, carrying it on the entire disk. And you can see that this recoiling black hole, actually, you can measure, it has a kick of 1,000 kilometers per second in this particular case. The thing that is very interesting about this simulation is that if you look very close to the recoiling black hole here and the gas that is arranged close to the recoiling black hole, so this is now a close view of the gas close to the black hole remnant, and you can see there are shocks. There are plenty of shocks, and these shocks tend to survive. And they were generated during the merger and prior to mergers. These shocks will cause a lot of light. And again, if you look at the light curve here, you'll see that there is, again, this characteristic dip and jump in the electromagnetic light curve. So the interesting thing is that the merger is not silent at all. Like it was predicted from earlier simulations where they didn't find any gas close to the merger. There is gas, and this gas is shocking. These shocks produce an electromagnetic signature, and the electromagnetic signatures jump up at post-merger. And this tends to last for quite a bit. We are still carrying on the simulations in this particular case, extending it to longer time, because obviously we want to know how long this signal will last into these states before the disk really actually equilibrate around the supermassive black holes that is recoiling along the z-axis in this case. So you see that this is important because it could be an important electromagnetic counterparts for post-merger signals of LISA. So it could be a post-cursor of a merger. Say that LISA will detect a merger via gravitational waves, and you can then follow electromagnetically the binary, localize and follow the binary if you know what kind of electromagnetic signature you should expect and how intense it should be. So,
Professor Manuela,
yes.
We have to wrap up this session because some
Yes.
of our speakers have to leave.
Yes, I'm going to close then. Thank you. So I'm going to just close here and just say that there are many more simulations that have been done for these very interesting scenarios that shows very interesting signature. I don't have any time, unfortunately, to present those, but let's say that the situation when the spins are not aligned looks much more messier. And there are shocks. In some cases, these things might resemble actually more TDE, tidal disruption cases, than actually the simulation, the orderly simulation that people had initially thought they would be. So I would just conclude here and to say that we do have really a very interesting era coming. It's not just because we have gravitational waves detectors, and obviously that's very important, for LIGO-India and LIGO and all the detector that looks for stellar mass black holes, but we have a lot of more observations coming in from also the electromagnetic spectrum that reveals that we have a very interesting universe when it comes to binary supermassive black holes. So I'm going to end it here, and if there is time for questions, I'll take questions.
Thank you, Manuela, so much for this very informative talk. Unfortunately, we are running very late. So in the interest of time, if you are around, please, there are a couple of questions in the chat. You may want to answer them. Otherwise, that's fine. So
Okay,
thank you so
I'll
much.
try.
And over to you, Devati.
Okay, so let's see. is that if a theoretical white hole were to merge with a black hole, would a gravitational waveform identical? Oh, is that for me?
Yeah, so you may kind of answer them in the chat if you are
Okay,
willing.
so
Yeah.
I didn't do any simulation of gravitational waveforms in this particular case. I don't know what to expect if you have a white hole with a black hole's merger in this particular case. So I would defer this question to, numerical relativists attending the call. I don't think anyone has ever done any simulation of that particular scenario. In terms of what happened in the stage, do the shock stage in an energy happen before or after the decoupling from the disk? So that's a good question. So it's when you talk about decoupling, I'm assuming that you're talking about the disk left behind with respect to binary. So you see that actually in our case, it's really that the disk is never really leaving the binary. So decoupling is not exactly the word I would use here because the disk is following the binary, except that the mini disk disappear. And as the mini disk shreds, what happened is that there is a lot of gas surrounding the system. As if I can go back really quickly to the images here. And so let's see. And what's happening is that actually here you can see it. The light is coming from this particular messy scenario because there are a lot of shocks here that forms, and these shocks are emitting a lot of light. So you can see here, for example, the luminosity emitted by these particular shocks that you see. So am I responding to the question? Do the shocks not happen before they do happen afterwards? Before the disappearance of the mini disks, most of the light is coming from actually the mini disks themselves. After the mini disks disappear, when the black holes are, it's roughly, in terms of m is 1,000 m, few binary orbit, 2-3 binary orbits before merger, then that's when the mini disks disappear, and that's when you see these shocks. And these
Thank you, Manuela. That's really informative. Again, and in the interest of time, I think we should move on. Thank you so much for joining, and thank you for your time, Manuela. It's been a pleasure to having you for this symposium.
Thank you very much for having me.
Thank you. So we are now moving on to the next session. So we have with us 4 early career researchers, and this is an interaction session where you can ask questions related to gravitational wave science. There are also other speakers who are from the previous session who are still around. If you want to ask some questions about their career trajectory or anything else, you can also ask them questions. So I am going to share my screen. I hope you can see my screen here. All right, so we will have in this session 4 early career researchers. So we have with us Dr. Shanika Galaudage from Northwestern University and Adler Planetarium. Shanika, are you able to unmute yourself?
Yep.
Okay. Okay. Hi. Good to see you. We also have with us Dr. Debashree Chattopadhyay. She is also currently postdoc at Northwestern University in the US. We have Dr. Debnandini Mukherjee from University of Birmingham in UK, and also Dr. Isabel Romero Shaw from Cardiff University in UK. So before we go on to the direct interaction session, we remind you of the code of conduct to be respectful and inclusive in your behavior during all the sessions. So a brief slide about the organizers themselves. So I'm Debarati Chatterjee. I just wanted to speak a little bit about my career trajectory as well. So currently I'm professor at IUCA, Inter-University Center for Astronomy and Astrophysics in Pune. I am a theoretical astrophysicist and working on modeling compact objects like neutron stars and white dwarfs, and as sources of gravitational waves. I'm also a member of LIGO-Virgo-Kavra collaboration and several other international collaborations. I am current chair of education and public outreach for LIGO-India project. I also do a lot of science communication. I'm currently director of the Pint of Science India Festival. And about my trajectory, so I did my PhD from Saha Institute of Nuclear Physics in Kolkata in India. I was also a DAAD fellow during my PhD. I did 3 postdocs before I joined as a professor. So I was Humboldt Fellow at University of Heidelberg in Germany. I was a postdoc at Observatoire de Paris in France, and a CNRS researcher at Laboratoire de Physique Corpusculaire in Caen in France. So yeah, I have diverse interests and I also speak many languages. I think you can see some of the pictures here. I also want to introduce Anuradha. Anuradha, if you're around, you want to tell us about your
Yeah.
trajectory?
Yeah. Hi, everyone. Yeah, I'm Anuradha Gupta. I'm an assistant professor at the University of Mississippi, USA. Yeah, I did my PhD from Tata Institute of Fundamental Research in Mumbai, India. And then I went on to do my first postdoc at IUCA, where currently Devriti is. And after spending a couple of years there, I moved to Pennsylvania State University in the USA for my second postdoc. And then after that, I'm a professor at the University of Mississippi since then. My interests are in black holes, neutron stars, their binaries, their astrophysics, astronomy, and testing general relativity and cosmology with gravitational wave. I'm a member of LIGO Scientific Collaboration and LISA Consortium, and basically I'm interested in anything with gravitational waves. Yeah, I think that's all for me.
Great, thanks a lot. So I think we can move to some of the early career researchers now. So Isobel, do you want to go first?
Sure. If my slide is up next, I'm happy to go first.
Okay. So just give me a second. All right, you can tell everyone about yourself.
Okay. Hi, everyone. I am Isabel. I am a Ernest Rutherford Fellow at Cardiff University, so I'm a postdoc basically. Prior to that, I originally did my PhD at Monash University in Melbourne, Australia, and then I moved back to the UK as a Herschel Smith Fellow at the University of Cambridge. So throughout my career, I've been mostly focused on looking at how binary compact objects meet each other and merge, producing these gravitational wave signals that we detect. And I am specifically focused on detecting and interpreting orbital eccentricity. So this is basically orbits that are not circular, close to the point that the binary merges. And that's pretty much what I spend most of my time thinking about. But anything that tells me something about either how binary compact mergers form and evolve, or what the environments that they evolve in are like, is interesting to me. In my free time, I like to do a lot of different activities. I like reading and I like running and weightlifting. And I also really enjoy doing art. And so I've put some pictures here that I have drawn or painted. I've chosen a selection of snail pictures for this slide, but I also draw other things. And yeah, that's me.
That's great. Thanks for telling everyone about yourself. Let's also have a look at what the other speakers who want to tell about themselves, and then we'll come back to you for more questions. So Dev Nandini, do you want to go next?
Yeah, hello everyone. I'm happy to go next. So yeah, I am a research fellow at the University of Birmingham currently. And so my PhD was at the University of Wisconsin, Milwaukee, in the US. And then before that, my bachelor's and master's were from University of Delhi in India. And then I've had two complete postdocs, one at the Penn State University, one at the University of Alabama in Huntsville, where I was working with NASA Marshall. And then I moved here in about a year and a half ago. So yeah, so I work in the area of gravitational wave data analysis and astrophysics. And I work with two different collaborations, the LVK, and I also started working with Lisa from my last postdoc. And in general, I was, yeah, I've also introduced a little bit of my early life I see here. So yeah, I grew up in small town India, just in case that's of significance or interest to people. And even though presently my parents live in a bigger city because that's where they were from, but when I was growing up, my parents were posted in a small town, so I had very limited opportunities and exposures growing up, and I did the best with what I had. And so I grew up in a small town called Asansol, and then I moved to Delhi for university. For hobbies, yeah, I love writing, poetry, as well as novels. I paint. I do photography. I travel. I try to make films as well nowadays. And I'm crazy about horror, thriller, podcast type of content. Thank you.
Thanks a lot, Devnandini, for telling us about your work and your background. So let's go to the next panelist here. So Debotri, are you able to unmute yourself?
Yeah. Okay. Thank you, Devarati, for introducing me. I'm Devotri Chattopadhyay. It's Devotri and Debaroti. Our names are very similar, but I write my surname as Chattopadhyay, which is the Sanskritized original version of the anglicized Chatterjee. I'm a postdoc at Northwestern University. I do mainly study stellar mass to intermediate mass black holes, neutron stars, radio pulsars, so really highly magnetized neutron stars, which are spinning very fast. They emit radio waves. They are another part of my research. And we just learned about supermassive black holes merging. So a way to sort of detect them is using this array of really fast spinning radio pulsars, but studying them in terms of populations and how to model them, that's another part of my expertise. So mainly I focus on gravitational waves and also the multi-messenger component sides of it. Here I show a diagram of what compact binaries life cycle would look like, which will start a sort of a detached zero-age main sequence star, and they can evolve and they can accrete mass onto each other, and then they become either a neutron star or a black hole, sometimes white dwarf, but I study more black holes and neutron stars, and then they merge. So all this entire life cycle, they can be also in different environments. Isabel mentioned eccentricity, so I also study dense environments, for example, or isolated environments. They are visible to the scientists from different perspectives. So not just gravitational waves when they merge, but the whole story before that. And sometimes even when they merge, if it's two neutron stars, or sometimes a black hole and a neutron stars, you will have a counterpart, an electromagnetic signal associated with that. So I like to take a holistic picture of this full story. I'm born and brought up in Calcutta, and that's a huge part of my culture that I carry everywhere. Then I did my PhD in Melbourne, then a postdoc in Cardiff, and now I'm in Chicago. I love doing classical dance. I'm a trained Indian classical dancer in Manipuri. I love reading novels, so both Bengali and English mainly. I love traveling, and I love hoarding saris and wearing saris. So I try to put a picture of me with a sari everywhere. Thanks.
Thanks a lot, Devotri. So we will introduce the last of our panelists, and this is Shanika. So Shanika, can you come on board?
Hello. Hi, everyone. I'm Shanika Gallagher, currently a postdoctoral fellow at both Northwestern University and the Adler Planetarium. So I have this really unique position where outreach is embedded into my postdoctoral fellowship. So 30% of my time is really about public engagement. And the 70% of my time, I work in the land of gravitational wave astrophysics. So to kind of walk you through where I've gone around the globe. So I did my PhD at Monash University with Isabel. We crossed paths there. Great. And also Debatri was also in Melbourne at the time at Swinburne. And I did my bachelor's and honours. So I should also say Melbourne, Australia is my hometown. So I grew up in Australia and did all of my education there. And so for my bachelor's and honours, I actually worked in a different field to what I work on now. I looked at X-ray pulsations from continuous gravitational wave candidates. So gravitational waves is in there, but it's more on the X-ray timing and things like that that I looked at. And then I decided, 27 years in Australia was enough. So I decided for my postdoc to move to the other side of the world, pretty much, to Nice, France. And I really just went with the opportunity of why not go to France and live on the French Riviera? That was probably one of the big motivators in taking that postdoc. But I was also working with Astrid Lamberts, who's an amazing scientist who I've learned a lot from, and I consider a very good role model for me in terms of both science and work-life balance, which I do carry with me to the US here. And right now, through my PhD and postdoctoral research thus far, my focus has been studying populations of compact objects. So majority of the time I look at black holes because that's what we have the most stuff of. But I have looked at neutron stars in comparison to what we see in radio observations to try and combine them. But most of my work boils down to, okay, we have these black hole observations. How can we explain their formation scenarios? How can we figure out what the structures we see in these population distributions, what do they map to in terms of astrophysics? And so that's my main interest in terms of research, but I'm also incredibly passionate about science communication. And so that's why this particular role was very enticing to me. So I'm just really going with like the motto I try to carry with myself that I think I learned probably during my first postdoc is just to go with the flow and not stress too much about what the future holds. It was, I think, a hard process to get to that mindset, but I absolutely love carrying that now.
Thanks a lot, Shanika. And she's also a great illustrator. I think you can see some of this here, but many of the graphics that are produced for press releases in LIGO collaboration come from Shanika, so great work. So I think we can pause here and look at some of the questions. So if people have questions, you can just pop it in the chat so you can ask anything, like just go ahead and ask these girls anything about their career trajectories, their work, what it takes to be a gravitational wave scientist, what it is like, moving around across the globe because they have done everything. Do we have questions in the chat? Because I don't
Yes,
see.
yeah, we have that. So maybe we can start with the first one. So I'll read that out for you and whoever feel comfortable answering them. So Nimera says, I'm a first year BSc physics student. Can you please enlighten me on the internship opportunities available for fresher related to physics?
I mean, any of you can unmute yourselves and
I just unmuted myself. That's okay. Yeah. If you're in India, I remember there used to be DST programs that you can apply every summer, although it might start a little later, probably second or third year of your bachelor's, if I remember correctly. And then you have to go through the process, and then you might get assigned to a host institute. Apart from that, I remember IUCA, where I did my internship. They would have every summer an open call. And there are other institutes like this as well. They might be better positioned to have all the details. The other thing we used to do is emailing particular people that we wanted to work with and just basically ask them questions and if they have any visiting positions for a short time. And yeah.
I can talk about some of the LIGO-India opportunities towards the end of this session. Yeah, but otherwise you can, because there are people from different countries here, so I think they can hear different perspectives. So that is great.
Yeah. Thank you, Devati. So the next question is from Andela Mogin. She says, I have a career-related question. How important it is how important is the choice of a master's degree for a career in gravitational wave astronomy? What kinds of courses should I be prioritizing?
I guess I can start with this one. I think if you have the opportunity to do a master's project that is related to gravitational waves, that's fantastic. But if you don't, getting any kind of like astrophysics skill that might be relevant to a gravitational waves project, or any kind of experience with the types of systems that you might be wanting to look at from a gravitational waves perspective. So binary evolution, stellar evolution, that kind of thing. Anything that's sort of tangentially related and will give you relevant experience would be ideal, I think.
Yeah, Shanika, go ahead.
I can add to that. I mean, my honors project was not in gravitational wave astronomy. The skill set was very different, but still in astronomy. But I think the main translatable skill that folks look for is coding experiences and ability to write science, which you do gain in an astronomy honors or masters. And so I think don't be too worried if like you do a master's or a honors in a different discipline, as long as you can translate those skills, which you absolutely can if you're doing something in astro, or even actually like maths and physics. I've seen people jump from physics to PhDs in astro. So that's definitely possible as long as you have those translatable skills built in those programs, which you do.
Yeah, Devanandi, go ahead.
Yeah, so actually the answer to that is it depends on a variety of things. It looks like you are not sure if you want to pursue a PhD. So in that case, there are other opportunities where you can assist labs or assist groups or be technical assistants where you basically assist the maintenance of codes or you write codes, in which case degrees, master's level degrees in coding, code management, software management would be more relevant. It kind of depends on which direction you want to go. But if you want to go the research PhD direction, then whether you need a master's or not depends on the country that you go to for a PhD. So mostly Europe, I could say India as well, but Europe, UK, etc. These countries expect you have a master's when you apply for PhD programs, but USA does not, because there you just have to have a bachelor's level undergrad to start what they call grad school, which is technically the PhD program. But then USA does expect you to have a 4-year bachelor's. So if you have a 4-year bachelor's, you don't need a master's. If you don't have a 4 years bachelor's, then it's best to have a master's or best to complete at least 1 year of master's. That's what I can say from my experience.
Yeah, thank you, Shanika, Devandi, and Isabel for chipping in for this question. Okay, so next question is from Janvi Mistry. They are asking, what kind of skills or background should be developed to do research in theoretical gravitational waves? And
I can try answering that. So I had a background in physics, and all honors and then masters, because astrophysics as a subject in India wasn't a thing at least at that point. But we obviously had special papers of GR, and hardcore theory subjects. Something we were forced to do was as well as chaos theory. I found it really interesting. Group theory, which is more on the particle side of things. But I think having a strong background in physics and maths beats a lot of the problems. Other skill sets you can acquire as you go along, as you work on the projects, but having that very base setup of classical mechanics, electrodynamics, and obviously general relativity will take you a very, very long way. As long as you have your basis strong, it's pretty easy as you go along with the project to build up other things over time. Yeah.
Yeah,
ahead.
Shanika?
I just want to add to the fact that so I did a like my bachelor's, I majored in both astrophysics and physics. In hindsight, if I could do it all over again, I'd probably want to major in astrophysics and maths instead. I feel like the theoretical gravitational wave aspect really does benefit from a more solid foundation in mathematics over physics itself, because the physics I did included like quantum physics and things like that, which didn't really apply to the research that I do now. So that's an aspect that you might want to think about. Just adding that in.
Yeah, definitely. Go ahead.
Yeah, I just wanted to add one more tiny thing to the great advice the ladies just had. That is computation. Yeah, and even for theoretical gravity, you might be running simulations, you might be working on waveforms, etc. So for all of those things, you need to have a very strong base in computation that really helps. So everywhere you get computation courses in Python, C, etc., anything involving AI nowadays, that's very useful. So definitely try to take those courses.
Yeah, and I'll just jump in with another final addition to all of these great points. I think something that is not really a formal skill, but one that you would benefit from developing is science communication, because even when you're interviewing for PhDs, you need to be able to explain what you've done and you need to be able to convince someone that you understood what you were doing. And so learning how to communicate science well is a really strong skill that will put you above other people, even if they have exactly the same grades as you.
Yeah, that's a very good advice. Okay, moving on. So Shamna Ghosh is asking, after a postdoc, how do research fellowships work? Could these be long-term positions, or is it another step towards a traditional professorship line? I'm more interested in joining a purely research position. US has national labs for that, but what are the options for other countries like India, France, UK?
Please
Yeah,
go ahead.
Isabel, go ahead. Yeah.
Yeah, I guess I can speak to this quickly, at least from the UK perspective. So typically the difference between a research fellowship and a traditional postdoc is that with a postdoc position, you're doing the work that somebody else has proposed. So your supervisor will have designed a project or have some research question that they want you to address, and you will do that research. With a fellowship, you propose the research yourself, and so you design the research program. The timescale of the fellowships can vary. So my first fellowship was 3 years long. My current fellowship is 5 years long. You can also get 8 year long fellowships in the UK, and potentially even longer ones. But the amount of work that you have to do to apply to those fellowships also increases with the with the length of the fellowship, because increased job security is something that a lot of people want, and so you have to provide a lot more motivation for why they should choose you. So that also tends to be another difference between a postdoc and a fellowship, is that I think in general, the amount of material you have to provide to apply for a fellowship is a little bit more. Yeah, I'm not sure if that answered the question fully.
So there is a follow-up question to that one. So if there is enough time, so are multiple postdocs required for research collaboration anywhere at all?
I suppose it depends what you mean by research positions. I think for a fellowship, for example, you can go into a fellowship straight from your PhD.
Maybe
For
she's asking like whether you need to do multiple postdocs to get like a tenured position.
Oh, I see.
Yeah.
Normally, yes. I think there are some very special cases where people haven't done a postdoc in between PhD and a professorship or a tenured position, but those tend to be quite rare.
Yeah, please, Deepnandi.
Yeah, I can provide some more input. So in the UK, at least, for fellowships, most of the fellowships we have in our field require at least 3 years of postdoc. And then most of them cut you off at a max of 7 to 8 years. There are a couple that don't have restrictions. So there are, I mean, the rules vary according to the fellowships, and I found that just like asking Google actually is pretty helpful. Yeah, Google AI does a good job of giving you the succinct answers from the very complex fellowship websites they have.
Yeah, great. Thanks. So the next question is from Annie. She's saying, I'll be graduating in MSc Astrophysics from UK this summer, but as an Indian resident in Bahrain, at the moment, it's hard to navigate what paths are open for me in these fields, as so far I'm trying in India. It's been not an ideal experience being an NRI. So is there any advice where I should apply for PhDs or research collab anywhere else, anywhere at all? So NRI means non-resident Indians, for people who are not aware of that.
I can try to take it up. So, I think even if you're an NRI, you're eligible to sit for the NET exam, which is like Pan India, and it's conducted, I think, twice every year. It used to be twice every year during my days by the central government. And you have to pass this exam. There's ranking, obviously, and you can basically have your own PhD fellowship or PhD money. You just need to, if you qualify that exam from the central government, but then you need to find an host institute and your supervisor who will work with you. But because it's your own funds, you're sort of in control of the situation a tad bit more. For abroad, I don't think NRI, this tag matters at all. So you can basically apply Europe, Australia. For the US, I think you need to sit for the qualifying exams. Um, yeah, I think that's kind of pretty much it. But yeah, if you're only looking at India, then I would strongly recommend to qualify the NET, the JRF, the Junior Research Fellowship NET exam.
Anybody wants to add anything? Maybe want to add anything? Okay. All right, moving on to the next question. Next question is from Giri. They ask, how do researchers decide whether to work in theoretical astrophysics or observational astrophysics?
I guess I can chime in the sense that I feel like I don't really belong in either bucket. I think most of us just go with what we find interesting in astrophysics, and then we somehow are thrown into that bucket. Like I think, yeah, no, so because like for me at least, I was like, I'm very interested in trying to understand what these black holes do and like what does that mean for like massive stars and like their progenitors and like what is that physics. And so I would say consider myself almost like a glorified data analyst at this stage of really just fitting models to data and then making interpretations from that. But in terms of it's like at the intersection of observation and theory and mapping those things together. So I would say you pick what you're interested in and it will fall under a bucket of theoretical astro. Someone else should chime in here.
Yeah, Isabel.
Yeah, maybe I can just say something because I think, particularly in gravitational waves, it's actually quite funny because for a long time, the people working in the field were all theoretical astrophysicists because we didn't see anything for so long. And I think people who are more senior in the field sometimes describe themselves as like a theoretical physicist who accidentally became an observational astrophysicist because we saw some things. So I would say, like, particularly in gravitational waves, the distinction between those two things is not as clear cut as it could be in other places. And the other thing I wanted to say was, as well as choosing what you're interested in, it also depends on the opportunities that you have. So if, say, there are a few PhD positions or postdoc positions you apply for, and then the only ones you're offered are the theoretical ones, well, that's probably what you're going to end up working in. But luckily, there's a lot of interesting science to be done in all of these areas. And as I said, there's quite a lot of overlap, actually. And so you can probably do a bit of both if you want.
Yeah, thank you, Shanika and Isabel. I can take the next question because I know something about that. So next question is, in gravitational wave source modeling, perturbative frameworks such as post-Newtonian, post-Minkowskian, and self-4 formalism are continuously being pushed to higher orders. On this note, beyond improving the accuracy of waveform templates used in match filtering and parameter estimation, what broader theoretical goals motivate these developments? Could you perhaps suggest some research group in India that are actively contributing to or aligned with these areas and whom I might consider approaching? Any guidance you could offer would be incredibly helpful. So I can start, but please chime in if you can. So for the post-Newtonian theory, post-Minkowskian, all this theoretical modeling for better waveform model, I think there's still many things to do. The motivation for the development is to cover the parameter space. Currently, what the systems we are observing through LIGO detectors are comparable masses, non-spinning, and so on. But if as our detectors become more sensitive, we will be seeing more corner cases or not so vanilla cases. And for that, we need to have accurate templates. So yeah, there is still many things to do in terms of theoretical modeling. And in terms of groups in India, so there is, so I know a few of them. So there is one group of KG Arun in Chennai Mathematical Institute in Chennai. And he's doing post-Newtonian theory, etc. So you may contact them. Another group is in Tata Institute of Fundamental Research, where I did my PhD. Professor Achimbidu Gopakumar, he is also doing some theoretical modeling. Other than that, there is a group at IIT Madras in Chennai, Professor Chandrakant Mishra. He's also doing similar works, and also a group at ICTS Bangalore, International Center for Theoretical Sciences in Bangalore, India. So these are few groups you may reach out to who are doing similar work as you described. I hope these are helpful.
I wanted to just mention that Shilpa, if you're still here and you want to add something to that, you can unmute yourself.
Yeah. Hi, Debarati, and hi, Sai. So, I mean, if you look back towards the history, if we haven't computed the 1 PN and 1.5 PN contributions, we wouldn't have actually measured the mercury precision. So if you do not compute the higher order terms, you will not be able to tell what new physics can come out of it. So that's one aspect of computing higher and higher order terms in post-Newtonian theory or even self-force cases. And so I'm also working on these sort of things, post-Newtonian theory. If you want, you may contact me as well.
Yes, I leave out to you, Shilpa. So there is a group in Saha Institute of Nuclear Physics in Kolkata. Shilpa is there, so you should also contact her.
Yeah, we should not forget the women faces we have on this panel. Okay, great. So I think, yeah, we can take a few more questions. Oh, wow.
Yeah, I see Devnan. Yeah, yeah.
Thank you.
But if anybody else wants to also chime in, so maybe I'll just read some of these questions, and if anybody else wants to answer that. So this is from Rutuja. They're saying, what are the crucial parameters we should consider while choosing from offered or applied PhD positions? Parameters I can think of: agreeability with the guide's research methodology, their research expertise relevant to our interested project, the subpar work environment, etc. I'm struggling to allot relevant importance to these three particular parameters. I am interested and have a few experiences in LIGO, in gravitational LIGO searches and LISA waveform generation.
I can try to chime in regards to the selection because I had an opportunity, two PhD opportunities in the US, one in France and one in Melbourne that I chose. And when I chose the Melbourne one, gravitational waves, there were exactly two detections. The big double neutron star detection was yet to come. So people were a little sort of in surprised that I picked Melbourne and gravitational waves. But what I went with, in a very Gen Z word, I went with the vibes. Just the vibes. Because PhD is something where the power dynamics, unfortunately, in academia, it's a little skewed. So you really need to get along with the person who's guiding you. As simple as that. For the US, you don't upfront always know who's going to be your guide. If you're already here, maybe sometimes, it depends on the universities. In France, I would have known, but I just had a feeling. I just had this sort of a gut feeling that this is going to work out, and I had an excellent time. So, above and over anything, I could not have known that gravitational waves were going to be this big. I joined my PhD 3 days later. There was the 170817 observation, so the double neutron star observation. It just happened. But even if it didn't happen, you have to ensure that you have a good time learning new things, right? So the topmost on that list is just you should get along with your PhD supervisor, and the rest will fall into place together, and others will have.
Go ahead, Shanika.
Yeah, Shanika.
Yeah, no, I strongly agree with that statement of needing to being in a work environment that supports you, because the environment can either make or break your love for a project, for example. One concrete way to do these things is while these potential PhD supervisors are interviewing you, you're really interviewing them as well to ask about, how they run their research group, what the dynamics are. You can ask them tough questions, because if they give you an answer that, is a red flag, then you don't want to work with them anyway. And the second thing is reach out to former postdocs and former PhD students of that group, because they should be able to, because they're no longer part of that group, they should be able to give you some pretty honest answers about what that group was like. So for me, I did those things. I talked to postdocs, talked to students, did all those things, and heard that Isabel was joining the group, for example. So I felt very comfortable joining, and I had a wonderful time. So these are really important things to do in terms of understanding the work environment you will be in. So yes, 100% agree with what Devatri said.
Thank you, Bati and Shanika. Yeah, please ask more questions related to career advice and so on in the chat. So there is a question which
Yes,
yeah,
sorry.
go ahead. Good.
I wanted to flash something in case somebody has to leave, because we are already at the hour. I just wanted to flash again some things. Wait a second. I will share my screen. Yeah, that's it. So I wanted to mention that we had great panelists for this session. Thanks a lot for your time. And I think all of them have been featured in LIGO India, because they are very, very good researchers and also great in science communication. So if you want to know more about them, you can go to the LIGO India social media. You can go to, so this is the link tree if you want to scan. And we are on Instagram, Facebook, X, and YouTube. So many of them have given interviews for behind the scenes. So they have talked at length about their research. So check them out. We also have other speakers. We had podcasts and we have had features about them. So check them out. And I just wanted to mention about the career opportunities. So if you go to the LIGO India website, so you click on the opportunities, so news and announcement opportunities, and here it brings you to this portal. So there is an application form for students that you can fill out, and you can write about what you want to do, like if it's theoretical physics, instrumentation, whatever interests you. And available projects are also listed here, so you can contact these people. So this is within India if you're looking for some projects, so you can do this. Yeah, so I just wanted to flash here. So this is the LIGO India YouTube channel. So you see that these are Gravity Matters. There's a full playlist talking about these early career researchers and all the great stuff they have done. And also feel free to check out our other, great talks on the LIGO India YouTube channel. And finally, I want to mention that these girls are also very outgoing and brave, and they didn't talk much about it. So I know personally that, I mean, we have featured them. So I know that Isobel wrote a book on planetemology, which we had featured. I don't know if you knew about it because, yeah, this is something I wanted to mention. Also, we featured, where is it? I think in the podcast, we had an episode about Isobel and Devotri together. And this was before they left for Antarctica. So they had this project Homeward Bound, and they visited Antarctica together. So they have done tons of adventure. So you can check out all this stuff on the LIGO India social media. And so I will just, yeah, I wanted to mention this here. So thanks a lot. Yeah. And do we want to take more questions or?
I know we were running late from the previous talks. So how long do we think we can stay for the session? Do you think?
Oh, thank you. Isabel has put the book on chat if you want to have a look. Oh, yeah, there's a coloring book about women in physics. Oh, wow. Thanks for sharing that. Yeah, I forgot about it. That's amazing. So you see that gravitational wave scientists, like particularly the women, are doing way more than just doing science. So that's amazing. So there are a few other questions. How long do we want to go on? So maybe like 5 more minutes.
Okay, that sounds good. And I'm sorry, we were running late, so hopefully you guys can stay for 5 more minutes. So there are some questions which Nandini is already answering, but maybe we can read out and further feel comfortable answering them. So this year I'm passing out a bachelor's degree in physics, and I want to build my career in gravitational astrophysics. So how have to proceed? How I have to proceed, and what are the top institutes in Europe and for astrophysics?
Maybe I'll just say quickly, I think the top institutes in Europe, it depends what specific topic you want to do. If you want specifically to do gravitational waves, then there are different institutes that we could recommend you than if you wanted to do X-ray astronomy, which I wouldn't know what to recommend you in that case. And also it depends really where in Europe you want to be. I mean, I think amongst the four of us, we can probably give you some advice about some countries that we have experience with, but maybe there are countries that we don't have any experience with really. But I suppose for gravitational wave related things, maybe a good thing to do would be to actually go on either the LIGO or Virgo websites and look at the universities that are actually involved in the collaboration. And that will give you some indication of where is doing kind of current research and being really active in the field. I can say, at least in the UK, I know that there are sort of three major gravitational wave institutes historically, which is Cardiff, Glasgow, and Birmingham. But there are now many more places in the UK that do a lot of really great gravitational wave research. And so if you look at the LIGO Virgo websites, you should be able to see these places.
I also know that there's a UK gravitational wave group as well. I saw somewhere. So people might also check out that for research in the UK.
Yeah, mostly around Southampton. Yeah. Yeah, and Portsmouth. Yeah, that's right. Okay, so I think we have to stop somewhere. So I think we can wrap up the session here. So maybe we can take a last screenshot together, a Zoom fee. Let me try to quickly. That's a word I invented, Shanika. Okay. All right. So if you all want to be in the Zoom feed, then you can put your cameras on. I will go to the gallery. So I think we have almost everyone. Okay. thanks to our audience also for joining us from everywhere. So there are people from all over the world, and yeah, curious students and researchers. So thanks to everyone who has been with us for the last 2 days. It was great. We had a lot of fun, as much as learned science and gravitational waves. So yeah, I think we can go for the selfie now, the Zoom-fee. So smile. Okay, one more. All right, I got that. So thanks again to everybody. If the interaction session panelists are okay with it, then we can also put this session on our YouTube channel. The recording, we can put it on the YouTube channel. And if any of the speakers are here, then if you share your slides with us, we can also put that on our website. Otherwise, we will put all the science talks anyway on the website. So, you know, people can go back to it and refer to it because there was so much great information. All the talks were amazing. So big round of applause for all our speakers and panelists. So thank you very much. Yeah, I would also like to acknowledge LIGO-India and Ayuka for supporting this initiative. Thanks to my co-organizer, Anuradha, for being there from 5:30 a.m. US time. So thanks a lot. Yeah, so I hope
Thank
that
you
this
for leading the way. Yeah. Thank you for leading the way. Yeah. So I'm happy to be part of this. Yeah.
great, great. Yeah, I think
One thing I think we have to, we are wanting to remind about the feedback form. Would you like to do that?
Yeah, sure. So we will send around a feedback form because this is the first time we are doing this. We learned a lot of stuff, and I think we can always have feedback about what we can do better next time. Do we want to go broader to other topics? I mean, of course, this was not exhaustive. We have so many great women speakers. We could not have everybody. So we had almost like one from every representative crew. But we can, of course, try to do this again. And yeah. So yeah, I will send around a feedback form so you can give us your comments. Yeah, if you want the material, so look at the LIGO-India social media and YouTube channel. So we will put up the talks, the recordings, and if the slides are available, we will also put them on the website. Okay. So yeah, with a heavy heart, I have to say good.
Yeah. Thank you so much for joining. Yeah, it was a wonderful experience. So I'll see you guys somewhere else, and all the best.
Thanks to everyone for being with us. Yeah, it was like a huge girls' party. So happy Women's Day, everyone. And yeah. All right. All right. Bye-bye.
Bye.
Thank you. Bye.
Thanks for being around.